Every ancient structure is a message from a world that no longer exists. The problem is that much of that message has been erased. Time removed names, languages, records, and memories, leaving only fragments behind, a wall without its builders, a temple without its beliefs, a city without the people who once filled its streets. Archaeology can recover stones, artifacts, and foundations, but recovering meaning is far more difficult. Why was this place built? What purpose did it serve? Why was it abandoned? Across the ancient world, countless sites continue to resist complete explanation. Not because there is no evidence, but because the most important pieces of the story may already be gone. And in that silence, some of history's greatest mysteries continue to survive. Circus Maximus is a giant scar carved into the heart of Rome, Italy. Long before modern stadiums, long before engineering software, long before crowd control science, this valley hosted the largest entertainment machine the ancient world had ever seen. At its peak, more than 150,000 and perhaps as many as 250,000 spectators could gather inside a structure stretching nearly 600 meters in length. Even today, archaeologists continue to debate how Roman engineers achieved some of its most remarkable technological feats. The greatest mystery is not the races themselves. It is the sophisticated engineering hidden behind them. Unlike many ancient monuments rediscovered after centuries of obscurity, Circus Maximus never completely disappeared. Ancient texts described it, medieval maps preserved its location, and generations of Romans lived around its ruins. Modern archaeological excavations during the 19th and 20th centuries gradually uncovered buried sections of seating structures, drainage systems, foundations, and racing infrastructure, revealing that the famous arena was far more technologically advanced than previously believed. The origins of Circus Maximus reach back to the Roman kingdom, possibly as early as the 6th century BC. Over centuries it expanded repeatedly under the Roman Republic and later the Roman Empire. By the reign of Emperor Trajan in the 2nd century AD, it had become the largest stadium ever constructed by the Romans. To appreciate its scale, comparison is essential. The modern Colosseum could hold roughly 50,000 spectators, while Circus Maximus may have accommodated 3 to 5 times that number. Its racing track measured approximately 600 meters long and around 140 meters wide, and the structure occupied nearly 8 hectares of urban space. Managing a crowd of this size remains challenging even with modern technology, yet Roman engineers achieved it nearly 2,000 years ago. One of the greatest unsolved engineering mysteries lies at the very beginning of every race. The starting gates, known as the carceres, appear deceptively simple, but in reality they may represent one of the most sophisticated pieces of mechanical engineering in the ancient world. A chariot race typically involved up to 12 teams. If all chariots started from a straight line, those positioned nearest the inside of the track would gain an enormous advantage. Roman engineers solved this problem by arranging the starting gates in a curved formation. This created a remarkable geometric challenge because each team needed to travel virtually the same distance to reach the first turn. The gate positions therefore had to be calculated according to precise geometric principles. Modern reconstructions suggest that the Romans designed the carceres using advanced surveying methods that compensated for the curvature of the track. Yet geometry was only part of the puzzle. The gates themselves appear to have opened simultaneously. Ancient accounts describe races beginning with remarkable synchronization. Such precision would have been impossible if attendants manually opened each gate one by one. Even a delay of a fraction of a second could determine the outcome of a race. This has led researchers to propose the existence of a centralized release mechanism. Some archaeologists believe ropes connected multiple gates to a single trigger system. Others suggest counterweights or mechanical locks may have been used. A more controversial hypothesis proposes a cascading mechanism that will list gates in an exact sequence designed to equalize starting conditions. The problem is that no complete example survives. No Roman engineering manual explains the mechanism, no technical drawings have been discovered, and no surviving text provides sufficient detail to reconstruct the entire system with certainty. The result is one of the most intriguing technological mysteries of the Roman world. The largest sporting arena on Earth may have relied upon a complex mechanical synchronization system that has vanished almost completely from history. Even today, engineers attempting reconstructions continue debating how such a mechanism actually worked. The mystery deepens when we consider the speed involved. Elite Roman racing chariots accelerated rapidly while carrying drivers standing on lightweight two-wheeled vehicles pulled by teams of horses. A mistimed gate release could easily cause collisions involving multiple teams moving at high speed. The reliability required was extraordinary, yet historical sources suggest the system functioned successfully for centuries. How Roman engineers maintained such precision remains largely unknown. Another remarkable mystery involves crowd management. Modern stadium designers use computer simulations to study crowd flow. Roman engineers possessed no digital tools, yet Circus Maximus routinely handled populations equivalent to a small city. Archaeological evidence reveals an intricate network of entrances, passageways, staircases, and seating sectors. These systems appear carefully organized to minimize congestion and distribute spectators efficiently. Researchers studying crowd dynamics have noted that several Roman design principles resemble concepts used in modern stadium architecture. Whether these solutions emerge through mathematical understanding or centuries of practical experimentation remains uncertain. Beneath the arena lies another engineering puzzle. Circus Maximus occupied a natural valley between the Aventine and Palatine hills. Such locations are vulnerable to flooding, particularly during heavy rainfall. Yet the stadium operated continuously for centuries. Excavations have uncovered extensive drainage systems connected to Rome's wider hydraulic infrastructure. Some channels maintained gradients so precise that water could flow efficiently across large distances without modern surveying instruments. The Romans achieved this using methods that remain only partially understood. How engineers measured elevation differences with such accuracy continues to fascinate historians of technology. The central barrier of the track, known as the spina, presents further mysteries. This long structure divided the racing circuit and served as the visual centerpiece of the arena. It carried obelisks, monuments, statues, shrines, and lap counting devices. Ancient sources describe rotating dolphins and eggs used to indicate completed laps. These markers appear simple at first glance, yet historians still debate how they operated. Were they moved manually? Did hidden attendants control them? Or could some have been linked to mechanical systems beneath the structure? The lack of surviving evidence leaves the question unresolved. The spina may have functioned as one of the earliest large-scale public information displays ever created. The construction itself presents additional unanswered questions. Building Circus Maximus required enormous quantities of stone, timber, brick, iron, and Roman concrete. Tens of thousands of workers likely participated across multiple generations. Modern estimates suggest that moving the required materials would have involved logistics comparable to major state infrastructure projects. Yet no complete construction records survive. No engineering handbook explains how materials were coordinated, and no project management documents reveal how labor was organized. The physical achievement survives, but the organizational knowledge largely does not. Perhaps the greatest mystery of Circus Maximus is the disappearance of the expertise that created it. The builders clearly understood geometry, surveying, structural engineering, hydraulics, crowd management, logistics, and mechanical design. Their accomplishments can still be measured scientifically. Their methods, however, remain frustratingly incomplete. What do you think? How did the Romans synchronize the starting gates of Circus Maximus with such remarkable precision nearly 2,000 years ago? Share your thoughts in the comments below. A small island in Lake Mälaren, Sweden, should never have become one of the most important cities in northern Europe. Yet between the 8th and 10th centuries, Birka transformed from a remote settlement into a trading hub connected to regions thousands of kilometers away. Merchants arrived carrying silver from the Islamic world, luxury goods from Byzantium, and products from across Scandinavia. For nearly 200 years, Birka stood at the center of a vast commercial network before suddenly disappearing from history. Today, archaeologists consider Birka one of the most important Viking sites ever discovered. But beyond its famous graves and trade routes lies a deeper mystery. Excavations reveal evidence of engineering, metallurgy, navigation, logistics, and urban planning far more sophisticated than many people associate with the Viking Age. The city was first identified in the late 17th century, but systematic excavations began during the 19th century, when archaeologist Hjalmar Stolpe uncovered thousands of artifacts and graves across the island of Björkö. Since then, decades of research have revealed an astonishing picture of Viking society. Yet the more evidence researchers uncover, the more questions emerge. And some of the biggest questions involve technology. One of the first mysteries is Birka's remarkable urban organization. Unlike many early medieval settlements that developed gradually and irregularly, Birka appears to have been deliberately planned. Archaeological surveys reveal designated trading districts, residential zones, workshops, harbour facilities, defensive structures, and organized street systems. For a city founded around AD 750, this level of planning is remarkable. Researchers estimate that Birka may have housed between 700 and 1,500 permanent residents, with seasonal populations potentially rising much higher during major trading periods. While these numbers seem modest today, they were significant for Scandinavia at the time. The question is how Viking planners achieved such organization. There are no surviving maps, no engineering manuals, and no written instructions describing how the settlement was designed. Yet the layout suggests careful surveying and long-term planning. Some historians compare Birka to early commercial centres such as Dorestad in the Netherlands or Hedeby in present-day Germany. However, Birka occupied a more isolated environment, requiring its inhabitants to solve logistical problems with fewer external resources. How they accomplished this remains uncertain. The harbour presents another technological puzzle. Everything about Birka depended on maritime trade. Without ships, the city would never have existed. Yet modern researchers face a challenge when attempting to reconstruct the original harbour because the landscape has changed dramatically over the past 1,000 years. Post-glacial rebound has gradually lifted the region, altering shorelines and water depths. This means that the coastline visible today is not the coastline Viking sailors used. Despite these changes, studies suggest Birka occupied an exceptionally strategic location. The site controlled access between inland Scandinavia and wider Baltic trade routes. Ships could move goods deep into the Scandinavian interior while remaining connected to international commerce. But selecting such an advantageous location may have required knowledge of navigation, seasonal water conditions, local geography, and long-term environmental patterns. Did Viking navigators possess a deeper understanding of regional hydrology than historians once believed? No one knows. The most fascinating mystery, however, may be Birka's metallurgy. Excavations have uncovered large quantities of iron slag, Furnace remains, crucibles, moulds, metalworking debris, tools, weapons, jewellery, and evidence of extensive industrial production. This was not occasional craftsmanship. This was organised manufacturing. At first glance, ancient iron production may seem simple. In reality, it represents one of the most difficult technological challenges any pre-industrial society could face. Producing usable iron requires temperatures approaching 1,200 degrees Celsius. Achieving such temperatures consistently demands careful control of fuel quality, airflow, furnace geometry, ore composition, and operating procedures. Even modern experimental archaeologists frequently struggle to reproduce ancient results. What makes Birka particularly intriguing is the apparent scale and consistency of production. Researchers have discovered evidence suggesting repeated large-scale iron working over extended periods. Significant quantities of slag indicate industrial activity far beyond the needs of a small local population. This raises an important question. How did Viking metalworkers repeatedly achieve successful results without thermometers, pressure gauges, chemical analysis, or modern metallurgical knowledge? The challenge becomes even more impressive when examining the finished products. Many weapons discovered at Birka demonstrate advanced forging techniques. Metallurgical studies reveal carefully controlled carbon content, sophisticated heat treatment, and complex welding methods. Some blades contain pattern-welded structures created by combining multiple iron and steel components. This process required extraordinary skill because even minor mistakes could ruin the entire weapon. Modern blacksmiths attempting to recreate pattern-welded Viking swords often spend years mastering the technique. Yet Birka's craftsmen produce such objects routinely. Researchers still debate how Viking smiths learned to control these processes so effectively. No written technical manuals survive, no instructional texts explain furnace operation, and no records describe apprenticeship methods. The products survive, but the knowledge largely disappeared. Even more surprising is the evidence for non-ferrous metallurgy. Archaeologists have recovered silver jewellery, bronze objects, decorative fittings, casting moulds, and evidence of precision metalworking. Some artifacts contain extremely intricate details requiring careful temperature control and advanced casting techniques. The production of these objects demanded not only technical skill but also access to raw materials arriving from distant regions. This connects metallurgy to another major mystery: trade. Thousands of Islamic silver coins have been discovered throughout Scandinavia, and Birka played a major role in this exchange network. Some silver originated thousands of kilometers away in the Abbasid Caliphate. This means Viking merchants maintained commercial links stretching from northern Europe to the Middle East. The logistical complexity is astonishing. Without modern maps, without compasses in widespread use, and without written navigation systems comparable to those used centuries later, goods, metals, textiles, and luxury items still moved across enormous distances with remarkable efficiency. Some researchers believe Viking navigators relied on sophisticated combinations of astronomical observations, environmental knowledge, landmark recognition, and accumulated generational experience. Exactly how effective these methods were remains a subject of debate. The mystery deepens when considering Birka's defences. A substantial defensive rampart protected parts of the settlement. Constructing such earthworks required organised labour, planning, resource allocation, and engineering knowledge. Although far smaller than Roman fortifications or the walls of Constantinople, the structure demonstrates that Viking leaders could coordinate large construction projects involving significant manpower. This challenges outdated stereotypes portraying Viking societies as politically simple or technologically unsophisticated. What do you think? Was Birka truly a unique Viking centre, or just one surviving glimpse of a far more advanced world we have lost? Share your thoughts in the comments below. Arany 1 cave is carved into the cliffs of Armenia's Arpa River Valley, hidden behind a narrow entrance in the Vayots-Dizor region. This seemingly ordinary cave has produced discoveries that forced archaeologists to rethink what people were capable of more than 6,000 years ago. Among its astonishing finds were the world's oldest known leather shoe, remarkably preserved human remains, and perhaps most surprising of all, the oldest complete wine production facility ever discovered. Yet the greatest mystery of Arany 1 is not what was found inside the cave. It is how people living during the Copper Age developed technologies so sophisticated that parts of their knowledge remain difficult to explain even today. The cave was first surveyed by local researchers, but major excavations began in 2007 under an international archaeological team. Almost immediately, the site started producing extraordinary discoveries. Layer after layer revealed artifacts preserved in conditions rarely seen anywhere in the world. Dry air, stable temperatures, and centuries of sheep dung covering ancient deposits create a unique environment that protected organic materials normally destroyed by time. What emerged was a snapshot of life more than 5 millennia old, and with every new discovery came new questions. The discovery that transformed Arany 1 into a global archaeological sensation was a complete wine production installation dating to approximately 4100 BC. Researchers uncovered a shallow clay basin used for crushing grapes, a channel designed to direct juice, large fermentation vessels, drinking cups, grape seeds, vine remains, and chemical traces associated with wine production. Radiocarbon dating placed the complex at roughly 6,100 years old. To understand how remarkable this is, consider the timeline. The winery was already operating before Stonehenge was built. It predates many Egyptian pyramids by more than 1,000 years, and it existed centuries before the rise of the great civilizations traditionally associated with advanced agriculture. At first glance, wine production may appear simple. In reality, it is an extraordinarily complex biochemical process. Successful fermentation requires the careful management of yeast activity, sugar content, temperature, storage conditions, and contamination risks. Modern winemakers monitor these variables using laboratory equipment and scientific analysis. The people of Arany 1 possessed none of these tools, yet evidence suggests they consistently produced wine on a scale beyond casual experimentation. This raises one of the cave's greatest mysteries. How did they acquire such detailed practical knowledge? Fermentation is invisible, and the microorganisms responsible cannot be seen with the naked eye. A single mistake can ruin an entire batch. Experimental archaeologists attempting to recreate ancient winemaking methods have repeatedly discovered how sensitive the process can be, as even slight variations in storage conditions dramatically affect results. Some researchers believe generations of accumulated observation may explain the achievement. Others argue that the level of organization visible in the winery suggests a tradition already mature by the time the facility was built. If that interpretation is correct, then the origins of this knowledge may be even older than Arany 1 itself. The cave may not represent the birth of winemaking technology. It may represent a stage in a much longer and largely invisible technological history. Arany 1 produced something rarely found in prehistoric archaeology: organic materials, including leather, wood, plant fibers, seeds, human hair, and even fragments of brain tissue. Normally, such materials disappear within centuries, yet thousands of years after their deposition, many survived in remarkable condition. The preservation rivals famous dry environment archaeological sites, such as Egypt's desert tombs and the naturally mummified remains found in the Atacama Desert. Scientists attribute part of this preservation to the cave's microclimate. Humidity remained unusually low. temperatures stayed relatively stable throughout the year, and air circulation reduced moisture accumulation. But this explanation creates another puzzle. Not all areas of the cave preserved materials equally. Certain chambers preserved organic remains far better than neighbouring sections only meters away. This suggests the existence of highly localized environmental conditions that researchers still do not fully understand. Did ancient occupants recognize these preservation zones? Did they intentionally place valuable objects in specific areas? Or was the pattern entirely accidental? The answer remains uncertain. In 2008, archaeologists uncovered what became one of the most famous artifacts ever found in the cave, a single leather shoe. Radiocarbon dating indicated an age of approximately 5,500 years. The shoe predates the Roman Empire by thousands of years, predates the Great Wall of China, and predates most surviving footwear on Earth. What surprised researchers was not merely its age, but the quality of its construction. The shoe was carefully shaped from a single piece of leather and fitted with leather laces. Its design appears practical, durable, and surprisingly efficient. Creating such an object required specialized knowledge of hide processing. Fresh animal skin rapidly decomposes, and without treatment, leather becomes brittle, rots, or loses structural integrity. This raises another unresolved technological question. What tanning methods were used? No written records survive, and no manufacturing manuals exist. Researchers can examine the finished product, but cannot fully reconstruct the exact techniques used to create it. Like many ancient technologies, the artifact survived while the knowledge behind it vanished. One of the most overlooked aspects of Archaeological is how effectively its occupants utilized the cave environment. The site appears to have been divided into functional zones. Some areas were used for storage, others were associated with ritual activity, certain chambers contained burials, and others housed production activities. This organization required a practical understanding of airflow, temperature variation, humidity levels, accessibility, and long-term preservation. Modern engineers use instruments to measure these variables. The inhabitants of Archaeological relied entirely on observation, yet their decisions often appear remarkably effective. The pattern resembles other ancient sites where environmental engineering seems more sophisticated than expected, including underground complexes at Derinkuyu in Turkey and storage systems developed by Andean civilizations in South America. How much of this knowledge was intentional engineering, and how much resulted from generations of trial and error, no one knows. Among the cave's most disturbing discoveries were several human skulls belonging to children. Some displayed unusual treatment after death. The context suggests ritual behavior, but archaeologists remain divided over its exact purpose. Several competing explanations have been proposed, including ancestor worship, ceremonial practices, mortuary rituals, and symbolic offerings. None has achieved universal acceptance. The finds demonstrate that Areni 1 was more than a production center. It was also a place of social and spiritual significance. Yet the beliefs associated with these practices remain largely invisible to modern researchers. The people of Areni 1 were not isolated cave dwellers. Evidence suggests participation in broader regional exchange networks. Materials found within the cave indicate connections extending across parts of the South Caucasus and neighboring regions. Such interactions required transportation routes, communication systems, and economic relationships. Yet almost none of this infrastructure survives. Archaeologists can see the products of these networks, but the networks themselves have largely disappeared. This recurring archaeological problem appears across the ancient world. Trade existed, technology moved, and ideas spread, but the mechanisms often remain hidden. What do you think? Was Archaeological truly the birthplace of winemaking technology? Or was it merely the surviving fragment of an even older tradition whose origins have been completely lost to history? Standing beside the Colosseum in Rome, Italy, the Arch of Constantine should not exist in the form we see today. Completed in 315 AD, the monument was built to celebrate Emperor Constantine's victory at the Battle of Milvian Bridge. At first glance, it appears to be a typical Roman triumphal arch, but modern archaeology has revealed something extraordinary. Much of the monument was not actually created for Constantine at all. Instead, enormous sections were removed from older imperial monuments, transported across Rome, modified and integrated into a completely new structure. The result was one of the most ambitious recycling projects in the ancient world. Nearly 17 centuries later, researchers still debate how Roman engineers accomplished this feat on such a massive scale. The arch rises approximately 21 meters high, stretches over 25 meters wide, and contains thousands of tons of stone, marble, and concrete. Yet the greatest mystery is not the monument itself. It is the engineering knowledge required to dismantle, transport, redesign, and reconstruct pieces of older monuments without causing structural failure. The monument remains, but the methods largely disappeared. Unlike lost cities buried beneath jungles or deserts, the Arch of Constantine was never truly lost. It remained visible throughout the Middle Ages and Renaissance. However, its greatest secrets only emerged during modern archaeological investigations in the 19th and 20th centuries. Researchers studying the sculptures noticed something unusual. The artistic styles did not match. Some reliefs were clearly older than others. Detailed analysis eventually confirmed that many decorative elements had originally belonged to monuments built under emperors Trajan, Hadrian, and Marcus Aurelius, some dating back nearly 2 centuries before Constantine. The arch was not simply a triumphal monument. It was an enormous architectural puzzle assembled from pieces of Rome's past. The most famous mystery surrounding the Arch of Constantine involves the practice known as spolia, the reuse of materials and artworks from older structures. At first glance, reusing stone may seem practical rather than mysterious. Ancient builders frequently recycled materials, but the scale seen here is almost unprecedented. Massive marble reliefs, statues, columns, and architectural elements were removed from earlier monuments and inserted into the new arch with remarkable precision. Many of these components weighed several tons, and some originated from structures located across different parts of Rome. This immediately raises a difficult engineering question. How were these enormous pieces safely extracted without destroying them? Modern demolition crews use hydraulic systems, steel supports, cranes, laser measurements, and advanced structural analysis. Roman engineers possessed none of these technologies, yet somehow they successfully dismantled monuments that had stood for generations. Even today, archaeologists cannot fully reconstruct the exact process. Once removed, the stone had to be moved. This may have been even more difficult than the dismantling itself. Some marble blocks likely weighed between 10 and 30 tons. Moving such objects through a crowded imperial capital would have required extraordinary planning. The Romans possessed wheeled vehicles, wooden rollers, rope systems, animal power, and treadwheel cranes. Historical sources describe these technologies, but no surviving document explains how they were specifically used during construction of the Arch of Constantine. Experimental archaeologists attempting to recreate Roman transport methods have discovered how challenging such operations truly are. A slight error in balance could crack a valuable marble relief. A minor miscalculation could overturn a transport platform. Every movement carried enormous risk. Yet the sculptures arrived largely intact. This suggests a level of logistical expertise that remains poorly understood. Of all the monument's mysteries, none is more fascinating than the large-scale recycling of marble. Modern engineers know that stone is not uniform. Marble from different quarries possesses different densities, mineral compositions, internal fracture patterns, weathering characteristics, and structural strengths. Two blocks that appear identical can behave very differently under load. Today, engineers analyze such materials using laboratories, computer simulations, and mechanical testing equipment. Roman builders had none of these tools. Yet the Arch of Constantine combined marble originating from multiple monuments, multiple construction periods, and potentially multiple quarry sources. This creates a remarkable technical puzzle. How did Roman engineers determine which pieces could safely be reused? How did they identify hidden weaknesses within ancient stone? How did they know whether a century-old marble block could continue supporting weight inside a new structure? Even more impressive is the precision with which these recycled components were integrated. Many pieces required modification before installation. Reliefs were reshaped, portraits were recarved, and architectural elements were resized. The process demanded accurate measurements and exceptional craftsmanship. A mistake could destroy irreplaceable artwork. The challenge becomes even greater when considering thermal expansion. Different stone types respond differently to temperature changes. Over centuries, these small movements can generate stresses capable of cracking structures. Modern conservation engineers routinely monitor such behavior, yet the arch has survived nearly 1,700 years. This raises an uncomfortable possibility. Roman builders may have possessed practical knowledge of stone behavior that was never formally documented and later disappeared. The arch's appearance hides another engineering achievement. Its three-arch design distributes enormous loads through a carefully balanced system of piers, vaults, and supporting walls. Roman builders understood that arches redirect weight outward and downward. However, the exact methods they used to calculate these forces remain uncertain. No surviving engineering manual explains how the builders determined dimensions, load distribution, or stress tolerances. Modern structural analysis reveals that even small changes in geometry could have significantly altered stability. Yet the proportions are remarkably effective. The monument has survived earthquakes, weathering, pollution, and centuries of urban development. Its continued survival suggests that Roman engineers possessed a sophisticated understanding of structural mechanics. Whether this understanding was mathematical, empirical, or both remains debated. Most visitors focus on the marble exterior. The true engineering secret may lie inside. Behind the decorative stone is a core composed largely of Roman concrete. Roman concrete continues to fascinate scientists because many ancient structures have survived far longer than expected. Studies have shown that certain Roman concrete mixtures become stronger over time due to chemical reactions involving volcanic materials. Researchers investigating Roman construction have identified complex mineral formations that continue developing long after the concrete hardens. Although significant progress has been made in understanding these materials, important questions remain unanswered. How were specific mixtures selected? How did builders control quality across massive projects? How much knowledge existed that was never recorded? The Arch of Constantine represents another example of this broader Roman concrete mystery. What do you think? Did Roman engineers possess advanced construction and material knowledge that was later lost to history, or are we simply underestimating what ancient builders could achieve with the tools available to them? Let us know your thoughts in the comments below. In the heart of Rome, Italy, stands a monument that most visitors see as little more than ancient stone column. Yet Trajan's column may be one of the greatest technological puzzles ever left behind by the Roman Empire. Completed in AD 113 and rising nearly 40 meters above the ground, the monument has survived almost 2,000 years of earthquakes, wars, pollution, and urban transformation. More astonishingly, it contains engineering features that continue to challenge archaeologists, architects, and historians today. The greatest mystery is not that the Romans built it. The greatest mystery is how they built it with such precision. Trajan's column was erected as part of Trajan's Forum to commemorate Rome's victory over the Dacians in modern-day Romania. Ancient sources describe the monument, but they provide remarkably little technical information about its construction. As a result, the monument itself has become the primary source of evidence, and the more closely researchers study it, the more questions emerge. The column consists of approximately 20 massive drums of Carrara marble, one of the most prized stones in the Roman world. Individual blocks are estimated to weigh between 25 and 40 tons, while some foundation elements exceed 50 tons. Carrara marble originated hundreds of kilometers away in northern Italy. Today, transporting such loads would require specialized trucks, cranes, and carefully engineered lifting systems. The Romans possessed none of these technologies, yet they somehow extracted, transported, shipped, unloaded, positioned, and assembled thousands of tons of stone with remarkable precision. Researchers believe the blocks were hauled from quarries to the coast, loaded onto ships, transported to Rome, and then moved through the city to the construction site. But the exact methods remain uncertain. Experimental archaeologists have demonstrated that moving stones of this size is possible using ropes, rollers, capstans, and human labor. However, reproducing the efficiency achieved by Roman builders remains extremely difficult. Even more remarkable is what happened once the stones arrived. The column was assembled vertically to a height equivalent to a modern 12-story building. Every marble drum had to be lifted into position and aligned perfectly with those below it. A small mistake near the base would have become a catastrophic error at the top. Yet after nearly 2,000 years, the structure remains almost perfectly stable. Ancient Roman engineers used cranes powered by treadwheels and pulley systems. Reconstruction suggests some cranes could multiply lifting force significantly. However, many scholars still debate whether known Roman lifting technology alone fully explains the placement of the heaviest elements at Trajan's column. The evidence suggests a level of project planning and mechanical engineering that may have exceeded what surviving Roman technical texts describe. Then there is the mystery hidden inside the monument. Most visitors never realize that the column is hollow. A spiral staircase containing approximately 185 steps winds through the interior all the way to the summit. The staircase was not carved afterward. It was integrated into the structure from the beginning. Each marble drum had to be hollowed out and shaped with extraordinary precision before being lifted into place. When stacked together, the staircase aligned perfectly from bottom to top. The challenge is difficult to appreciate until one considers the tolerances involved. A misalignment of only a few centimeters in one block could have rendered the entire staircase unusable. Yet the interior remains functional nearly 20 centuries later. No surviving Roman blueprint explains how such accuracy was achieved. However impressive these mysteries may be, they're overshadowed by the feature that has fascinated scholars more than any other. Wrapped around the column is a continuous carved narrative measuring approximately 190 to 200 meters in length if unrolled into a straight line. It contains more than 2,500 human figures. It depicts military campaigns, engineering works, fortifications, river crossings, diplomatic meetings, religious ceremonies, logistics operations, and combat scenes. No other monument of the ancient world presents a visual narrative on such a scale. The relief effectively functions as an enormous stone documentary carved around a cylindrical surface. This is where the technological mystery becomes truly extraordinary. Imagine attempting to design a 200-meter-long visual story that spirals upward around a giant cylinder. Every scene must connect logically to the next. Every figure must maintain consistent proportions. The narrative must remain readable despite constantly curving around the monument. And the entire composition must fit perfectly onto a surface that becomes progressively harder to reach as construction rises. Today, designers would use digital modeling software, three-dimensional visualization tools, laser measurements, and computer simulations. The Romans had none of these. Yet the relief demonstrates remarkable organizational consistency. The scale of figures subtly increases toward the top of the column. This adjustment was likely intentional. Without it, upper scenes would appear too small when viewed from the ground. This suggests Roman artists were not simply carving decorative images. They were actively compensating for optical distortion. In other words, they understood principles of visual perception that allowed them to manipulate scale across a structure nearly 40 meters tall. How they calculated these adjustments remains unknown. Some scholars propose that detailed master drawings were prepared before carving began. Others suggest grids, measurement systems, and proportional planning techniques were employed throughout construction. However, no surviving evidence reveals exactly how the project was coordinated. The logistics alone are staggering. Thousands of figures, hundreds of individual scenes, and a narrative extending almost 200 meters were all executed without modern drafting technologies. Comparisons help illustrate the achievement. The Bayeux Tapestry, created roughly 1,000 years later, contains about 70 meters of embroidered narrative. Trajan's column contains nearly 3 times that visual length carved directly into marble. Even many modern public monuments do not approach this level of narrative complexity. Yet another puzzle emerges when researchers examine visibility. Much of the relief near the top cannot be clearly viewed from ground level. This raises a perplexing question. Why invest enormous resources carving details that ancient spectators could barely see? Some historians argue that nearby buildings once provided elevated viewing platforms. Others suggest the monument functioned as a symbolic statement of imperial power rather than a practical storytelling device. Neither explanation fully resolves the issue. The upper relief contains astonishing detail despite its limited visibility. It is almost as if the craftsman continued carving for reasons beyond human observation. Adding another layer of mystery, traces suggest the relief may originally have been painted in bright colors. If true, the monument would have looked dramatically different from the white marble column visible today. Thousands of figures may once have been highlighted with pigments. Weapons, clothing, banners, and architectural features could have appeared vividly colored. Nearly all of that evidence has disappeared. What survives is only a fraction of the original visual experience. Finally, there is the question of durability. Many ancient monuments collapsed centuries ago. Trajan's column remains standing. Its marble blocks continue to support enormous weight. Its relief remains legible. Its staircase remains accessible. Its structure remains remarkably stable. The monument demonstrates mastery of quarrying, transportation, mechanics, architecture, geometry, visual design, project management, and large-scale construction. Yet the technical knowledge behind these achievements largely vanished. No complete engineering manual survives. No construction handbook explains the lifting systems. No project records describe how thousands of workers were coordinated. No blueprint reveals how the spiral narrative was planned. The stone survives, the knowledge does not, and that may be the greatest mystery of Trajan's column. What do you think? Did Roman engineers possess advanced construction techniques that have been lost to history, or can everything about Trajan's column ultimately be explained through skill, organization, and ingenuity? Let us know your thoughts in the comments below. Zalisa, central Malawi. Scattered across a quiet landscape are the remains of an ancient community that left behind no monumental pyramids, no giant stone temples, and no written records. Yet hidden beneath the soil lies evidence of a technological achievement that continues to puzzle archaeologists. Ancient furnaces, thousands of kilograms of slag, and signs of iron production sophisticated enough to challenge assumptions about pre-industrial engineering. The greatest mystery is simple. How did the people of Zalisa master one of the most difficult technologies of the ancient world without any known scientific instruments? Archaeological investigations at Zalisa revealed settlement remains, pottery, ironworking debris, furnace fragments, and large accumulations of slag. These discoveries showed that Zalisa was not merely a farming village. It was also a centre of specialised production where iron technology played a significant role in daily life and regional exchange. But every discovery created new questions. The more archaeologists learned about Zalisa, the more mysterious its technology became. Of all Zalisa's technological puzzles, none is more fascinating than its iron production. Today, producing iron requires carefully controlled industrial systems. Modern blast furnaces rely on precise measurements of temperature, airflow, fuel ratios, and chemical composition. Ancient ironworkers possessed none of these tools, yet they somehow achieved results that required remarkable engineering skill. To transform iron ore into usable metal, furnace temperatures typically must exceed 1,100 degrees Celsius and often approach 1,200 degrees Celsius. At such temperatures, every variable becomes critical. A slight reduction in airflow can dramatically lower furnace efficiency. Too much oxygen can damage the process. Poor charcoal quality can prevent the necessary temperatures from ever being reached. Modern experimental archaeologists attempting to recreate ancient iron production frequently discover that success is far from guaranteed. Even when researchers possess complete knowledge of metallurgy, reproducing ancient smelting techniques often requires multiple failed attempts. This makes Zalisa especially intriguing. The people who operated these furnaces had no thermometers, no chemistry textbooks, no engineering diagrams, and no mathematical models. Yet the surviving slag demonstrates that their furnaces worked, and they worked repeatedly. The volume of waste material found at ancient African ironworking sites often indicates production on a scale far beyond occasional household use. Some regions of sub-Saharan Africa produced thousands of tons of iron over centuries, requiring sustained technical expertise across generations. The question is not whether they could make iron. The evidence proves they could. The mystery is how they learned to do it so consistently. How many centuries of experimentation were required? How many failures preceded success? And how much of that knowledge vanished when the furnaces fell silent? The furnace remains found throughout southern and eastern Africa have revealed something unexpected. Some ancient furnace designs appear capable of generating powerful airflow using natural physical principles. Instead of relying entirely on bellows, certain furnace systems may have exploited pressure differences, convection currents, and chimney effects. In simple terms, the furnaces themselves helped create the airflow needed to sustain combustion. This is where the mystery deepens. Modern computational studies show that airflow inside a furnace is extremely complex. Tiny changes in height, wall thickness, opening size, or internal shape can dramatically affect performance. Yet many ancient furnaces appear surprisingly efficient. Some researchers have compared these systems to naturally ventilated industrial reactors. If Zalisa's metal workers intentionally designed furnaces around these principles, they possessed a practical understanding of thermodynamics centuries before the science was formally described. If they discovered these principles through trial and error, their achievement may be even more remarkable. Either way, the knowledge behind the designs has largely disappeared. Building a furnace capable of reaching over 1,100 degrees Celsius requires more than fuel. It requires the right materials. Not every clay can survive repeated exposure to extreme heat. Many crack, others deform, and some collapse entirely. The builders of Zalisa somehow selected materials capable of enduring these conditions. This suggests an advanced understanding of local geology. Perhaps they identified specific clay deposits through generations of experimentation. Perhaps they possessed traditional knowledge passed between master craftsmen. We do not know. The furnaces remain, but the instructions are gone. The situation resembles another famous mystery. Roman engineers created concrete structures that survived nearly 2,000 years. Modern scientists only recently began understanding some of the chemical processes responsible for that durability. Zalisa presents a similar puzzle. The technology survived, but the knowledge behind it largely disappeared. Iron production consumes enormous resources. Charcoal is especially important. Producing a single kilogram of iron often requires many kilograms of charcoal, which in turn requires large quantities of wood. This creates a major logistical challenge. Where did Zalisa obtain sufficient fuel? How was wood harvested? How far was it transported? How are ore sources identified and exploited? Archaeological evidence can reveal the existence of iron production, but reconstructing the entire supply chain is much harder. The more iron produced, the more complex the organization required. Workers had to gather ore, others produced charcoal, furnaces required construction and maintenance, finished metal needed distribution. All of this suggests a level of social coordination that remains only partially understood. Artifacts recovered from Zalisa show recurring patterns in manufacturing. Pottery styles remain surprisingly consistent. Metalworking techniques appear standardized. This may seem insignificant. In reality, consistency is often evidence of sophisticated knowledge transfer. Modern factories use manuals, measurements, and quality control systems. Ancient communities relied on entirely different methods. How did Zalisa maintain technical standards across generations? Did specialist guilds exist? Were apprentices trained through highly structured systems? Did certain families control metallurgical knowledge? Archaeology offers clues, but few definitive answers. What survives are the products. The educational system that created them has vanished. Perhaps the most overlooked mystery is whether Zalisa's technology developed independently. Ironworking traditions existed across large parts of Africa. Some scholars believe innovation spread through extensive networks connecting distant communities. Others argue that local experimentation played a greater role. The truth may involve both. Ideas can travel hundreds of kilometers. Knowledge can spread without leaving written records. A furnace design perfected in one region might gradually appear in another. If this happened, Zalisa was not merely a settlement. It was part of a much larger technological landscape stretching across ancient Africa. Unfortunately, the routes through which knowledge travelled remain largely invisible. Goods leave archaeological traces, ideas rarely do. What do you think? Was Zalisa's iron technology developed independently, or was it part of a lost network of knowledge that once connected ancient Africa? Share your thoughts in the comments below. Few ruins in human history reveal a technological mystery as astonishing as the baths of Caracalla in Rome, Italy. Built nearly 18 centuries ago, this gigantic bathing complex functioned like a self-contained city, powered by engineering principles that remain only partially understood today. The stone walls still stand, but the technology behind them has largely vanished. The baths of Caracalla were constructed between AD 212 and AD 216 under the Roman Emperor Caracalla. Although historians have studied the site for centuries, systematic archaeological investigations accelerated during the 19th and 20th centuries, uncovering an immense underground network hidden beneath the visible ruins. What researchers found transformed the site from a simple public bath into one of the most sophisticated technological systems of the ancient world. Most visitors see enormous brick walls rising above Rome's landscape. But what they do not see is the machine buried underneath. At its peak, the baths of Caracalla covered approximately 11 hectares, making it one of the largest bathing complexes ever constructed by the Roman Empire. Ancient sources suggest that thousands of people could use the facility daily, and some modern estimates place daily attendance between 6,000 and 8,000 visitors. To modern eyes, the baths appear to be a collection of impressive ruins. To engineers, however, they represent a problem. How did ancient builders create and operate a structure that functioned like a giant climate-controlled complex nearly 2,000 years before electricity, boilers, pumps, computers, or modern engineering instruments existed? The greatest mystery begins with heat. Today, heating a modern shopping mall requires massive infrastructure. A large commercial complex depends on electrical systems, computerized controls, ventilation equipment, sensors, insulation materials, and maintenance teams working continuously behind the scenes. Yet the baths of Caracalla maintained enormous hot rooms, warm rooms, steam chambers, pools, and public spaces every day. The Romans achieved all of this using fire. Archaeological excavations have revealed one of the most remarkable heating systems ever built in the ancient world, the hypocaust. At first glance, the concept seems simple. Beneath the floors stood thousands of small brick columns supporting elevated surfaces. Massive furnaces generated hot air that flowed through these underground spaces. The heat then travelled upward through hollow wall channels before escaping through carefully designed vents. In theory, it sounds straightforward. In practice, it should have been extraordinarily difficult. Modern engineers know that heating large buildings evenly is one of the most challenging problems in climate control. Airflow constantly changes, heat naturally escapes, different rooms require different temperatures, and minor design errors can create hotspots, cold zones, and severe inefficiencies. Yet evidence suggests the baths of Caracalla operated successfully for centuries. Some rooms needed temperatures exceeding 40 degrees Celsius, others had to remain warm but comfortable, massive pools required heated water, steam rooms demanded high humidity, and public halls needed stable conditions despite thousands of visitors entering and leaving throughout the day. All of these environments existed simultaneously within the same structure. How? No thermostats have been found. No pressure gauges existed. No temperature sensors existed. No surviving technical manuals explain how Roman engineers balanced airflow across such a vast network. Researchers studying reconstructed hypocaust systems have discovered that even small changes in furnace output, tunnel dimensions, or ventilation openings can dramatically alter performance. Maintaining stable temperatures requires surprisingly precise control. The mystery becomes even more remarkable when scale is considered. Archaeologists estimate that dozens of furnaces operated continuously beneath the complex. These furnaces consumed enormous quantities of wood fuel, and some calculations suggest that many tons of wood may have been required every day to maintain full operation. This raises another unanswered question. How did Roman administrators sustain such an energy-intensive system year after year? The logistics alone were staggering. Fuel had to be harvested, transported, stored, distributed, and burned efficiently. Furnace workers had to monitor temperatures around the clock. Ash had to be removed, and air passages had to remain clear. The baths were not simply a building. They were an industrial operation. In many respects, the underground infrastructure resembles a modern power plant hidden beneath a public recreational centre. Excavations have revealed kilometres of service corridors beneath the baths. Workers moved through these tunnels carrying fuel, maintaining furnaces, controlling operations, and servicing the facility without disturbing visitors above. The hidden network is so extensive that some archaeologists compare it to the service infrastructure found beneath modern airports or stadiums. What makes this comparison remarkable is the difference in technology. Modern facilities rely on electric lighting, reinforced concrete, computer modelling, and mechanical equipment. The Romans had none of these advantages, yet they constructed a system that performed many of the same functions. The heating mystery is only the beginning. The baths also depended on one of the largest water management systems in ancient Rome. A dedicated branch of the Aqua Marcia aqueduct supplied the complex with enormous volumes of fresh water. Millions of litres may have circulated through pools, fountains, reservoirs, and service channels. Managing water on such a scale would challenge many cities even today. The Romans somehow coordinated cold water, warm water, hot water, wastewater, drainage, and storage simultaneously. Everything operated using gravity. No electric pumps existed. No mechanical motors existed. No computerized monitoring systems existed. Yet the system functioned with extraordinary reliability. Researchers continue to debate how Roman engineers optimized water flow, pressure control, and maintenance across such a massive installation. Another mystery involves construction itself. The surviving ruins reveal walls reaching heights exceeding 30 meters. Vast vaulted ceilings once covered enormous interior spaces, and giant halls rivaled the dimensions of some medieval cathedrals built more than 1,000 years later. Many of these structures relied on Roman concrete. This material remains one of the most studied ancient technologies in the world. Modern laboratory analysis has identified volcanic ash known as pozzolana as a key ingredient. However, scientists continue investigating why Roman concrete often demonstrates durability that rivals or exceeds many modern mixtures. The baths of Caracalla survived invasions, earthquakes, weathering, stone robbing, and nearly 18 centuries of exposure. Large portions still remain standing. Many modern concrete structures struggle to achieve comparable longevity. The exact combination of materials, construction methods, curing techniques, and engineering practices remains a subject of active research. Some knowledge may have been lost forever. What do you think? Did Roman engineers possess scientific knowledge far beyond what history has preserved? Or are we simply underestimating the ingenuity of ancient technology? Let us know your thoughts in the comments below. Kaupang, southern Norway. More than 1,200 years ago, a small settlement on the edge of a fjord became one of the most important trading centres in the Viking world. What makes it mysterious is not its size, it is the technology hidden behind it. Because long before compasses, navigation charts, engineering schools, or industrial shipyards, the people of Kaupang somehow built a system capable of connecting Scandinavia to lands thousands of kilometers away. And even today, researchers still cannot fully explain how they achieved it. The site of Kaupang was identified in the 19th century, but large-scale archaeological excavations beginning in the 1950s and continuing into the 21st century revealed its true significance. Researchers uncovered workshops, imported goods, trading equipment, ship-related artifacts, metalworking debris, and evidence of a thriving urban centre that existed from approximately 800 to 950 CE. The discoveries transformed Kaupang from a forgotten settlement into one of the most important Viking sites ever found. Yet every excavation seemed to create more questions than answers. At first glance, Kaupang appears to be a modest Viking settlement. In reality, it was connected to an enormous international trade network. Archaeologists have discovered objects originating from regions separated by thousands of kilometers. Glass beads likely arrived from the Middle East. Silver coins came from the Islamic world, and jewelry styles reflect influences from across Northern Europe. Various imported materials suggest regular contact with distant regions connected through rivers, seas, and overland routes. The distances involved are astonishing. A merchant leaving Kaupang could theoretically travel through the Baltic Sea, enter the river systems of Eastern Europe, reach the Black Sea, and eventually access trade routes leading toward Constantinople and the Abbasid Caliphate. Some of these journeys exceeded 3,000 kilometers. For comparison, this would be roughly equivalent to traveling from London to Cairo. The mystery is not that trade occurred. The mystery is how Viking merchants maintained such extensive networks without modern navigation systems, detailed maps, or centralized communication. Even small navigational errors at sea can accumulate dramatically. A vessel deviating by only a few degrees over hundreds of kilometers may miss its destination entirely. Yet, Viking trade flourished. How? No one knows for certain. Excavations at Kaupang have revealed scales, weights, and evidence of standardized trading practices. This may sound ordinary, but it is not. Trade requires trust. Trust requires measurement. Measurement requires standards. Modern economies rely on official systems of calibration and regulation. The Vikings had no equivalent institutions. Yet many weights discovered across Viking trading centers demonstrate remarkable consistency. Similar systems appear at Kaupang, Birka in Sweden, and Hedeby in present-day Germany. Researchers have suggested that merchants operated within a surprisingly sophisticated economic framework. Silver was often valued by weight rather than by coin denomination, which meant accuracy was essential. A small error repeated across hundreds of transactions could create enormous losses. The question remains unresolved. How are standards maintained across vast distances and multiple cultures? Who enforced them? And how did knowledge spread so effectively throughout the Viking world? Among the most important discoveries at Kaupang are the remains of metalworking activities. Archaeologists have uncovered slag, furnaces, molds, tools, and evidence of large-scale production. Ironworking was one of the most technologically demanding activities of the early medieval world. Producing high-quality iron required temperatures approaching 1,200 degrees Celsius. Maintaining those temperatures required careful control of furnace design, fuel quality, airflow, and ore composition. Modern metallurgists use instruments to monitor these variables. Viking smiths had none. Yet many surviving Viking artifacts display impressive quality and consistency. Experimental archaeologists attempting to recreate ancient iron production have repeatedly discovered that seemingly simple furnaces often conceal sophisticated engineering principles. Airflow dynamics alone can determine whether a furnace succeeds or fails. The people of Kaupang clearly understood these principles. The mystery is that they left almost no written explanation of how they learned them. Their technology survives, but their technical manuals do not. This may be the greatest mystery of all. Without extraordinary ships, Kaupang could never have existed. Everything depended on shipbuilding. Trade depended on ships. Communication depended on ships. Exploration depended on ships. The entire Viking world depended on ships. And yet Viking shipbuilding remains one of the most remarkable engineering achievements of the ancient and medieval worlds. Consider what these vessels accomplished. Viking ships crossed the North Sea, reached Iceland, colonized Greenland, and reached North America nearly 5 centuries before Columbus. The voyage from Norway to Iceland alone covers roughly 900 kilometers of open ocean. Crossing from Greenland to Newfoundland involves navigating some of the most dangerous waters in the North Atlantic. Modern sailors possess GPS, weather forecasts, radar, and satellite communications. The Vikings possessed none of these technologies, yet they succeeded. How? Part of the answer lies in the ships themselves. The famous clinker-built construction method involved overlapping wooden planks fastened together with iron rivets. This created hulls that were simultaneously strong, flexible, and surprisingly lightweight. Modern naval architects have long admired the design. Unlike rigid hulls that resist waves, clinker-built ships could flex slightly with the movement of the sea. This reduced structural stress and improved survivability in rough conditions. What astonishes researchers is the precision involved. A typical Viking ship might contain thousands of individual components. Each plank had to be shaped correctly. Each frame had to match the vessel's geometry. Weight distribution had to remain balanced. Hydrodynamic performance had to be maintained. A minor mistake could compromise the entire vessel. Yet archaeological evidence suggests Viking shipbuilders achieved extraordinary consistency. The famous Oseberg ship, discovered in Norway and dated to approximately 820 CE, demonstrates craftsmanship of exceptional quality. The Gokstad ship, built around 890 CE, exhibited such advanced seaworthiness that a replica successfully crossed the Atlantic in 1893. That achievement shocked many observers. A vessel based on a design over 1,000 years old had proven capable of surviving an ocean crossing. The implications were profound. It suggested Viking naval engineering was far more advanced than previously assumed. But this raises an even larger mystery. How did Viking shipbuilders design their vessels? No blueprints survive. No engineering calculations survive. No construction manuals survive. No detailed written descriptions explain the process. Modern shipyards rely heavily on mathematics, drafting, and technical documentation. The Viking system appears to have relied largely on transmitted knowledge passed from master to apprentice, generation after generation. This creates a paradox. The ships clearly required sophisticated engineering understanding, yet the knowledge behind that engineering vanished almost completely. Researchers can measure the ships, reconstruct the ships, and even sail replicas of the ships, but they still cannot fully reconstruct the intellectual process that created them. The technology remains visible. The design methodology remains largely invisible. Kaupang's location appears almost perfectly chosen. The settlement sat near protected waters while maintaining access to major maritime routes. It provided natural advantages for trade, transportation, and defense. This raises another question. How did Viking leaders identify such strategic locations? Choosing an effective harbour requires understanding tides, currents, shelter, accessibility, and regional geography. These are not random decisions. Modern port planners use extensive surveys and environmental studies. The people of Kaupang relied on observation and experience, yet their choice proved remarkably successful. Some researchers believe Viking communities possessed generations of accumulated maritime knowledge that functioned as a sophisticated practical science. If true, much of that science disappeared with the end of the Viking Age. What do you think? Were the ships of Kaupang simply the product of experience and trial and error, or did Viking shipbuilders possess a deeper engineering understanding that has been lost to history? Let us know your thoughts in the comments below. Gamla Uppsala lies approximately 5 kilometers north of modern Uppsala in central Sweden. Today, it appears as a peaceful landscape dominated by 3 enormous burial mounds, but archaeological excavations have revealed that this site was once one of the most important political and religious centres in Scandinavia. The first systematic investigations began in the 19th century, while major archaeological excavations during the 20th and 21st centuries uncovered royal halls, ritual structures, ancient roads, workshops, and evidence of large-scale construction projects. Ground-penetrating radar, geophysical surveys, aerial mapping, and modern excavation techniques continue to reveal previously unknown features hidden beneath the landscape. What researchers discovered raised an unexpected question. How did a society living more than 1,500 years ago create engineering projects on a scale that would challenge even many medieval kingdoms centuries later? Unlike famous ancient mysteries such as the Egyptian pyramids or Stonehenge, Gamla Uppsala is not known for giant stone monuments. Its mysteries are hidden within earthworks, timber architecture, logistics systems, and construction techniques that remain only partially understood. The most recognizable features of Gamla Uppsala are the 3 monumental burial mounds known as the Royal Mounds. Each mound rises roughly 9 to 10 meters high and measures approximately 55 to 70 meters in diameter, and archaeologists date their construction to the 5th and 6th centuries AD. At first glance, they may appear simple compared to the pyramids of Egypt, yet engineering calculations suggest otherwise. Building a single mound required moving thousands of tons of earth, clay, gravel and turf, and the 3 mounds together represent one of the largest earth-moving projects in Northern Europe during the migration period. The challenge becomes even more impressive when considering the available technology. No wheeled construction equipment existed, no iron excavators existed, and no modern surveying instruments existed. Researchers estimate that tens of thousands of cubic meters of material had to be collected, transported, shaped, and compacted. Even today, civil engineers understand that large earthen structures require careful control of slope angles and drainage. Poorly designed mounds erode quickly, yet after nearly 15 centuries the royal mounds remain remarkably stable. How their builders achieve such durability remains an active subject of investigation. Perhaps the most surprising discoveries at Gamla Uppsala are the remains of gigantic wooden halls. Excavations have revealed structures exceeding 50 meters in length, and some researchers compare them to royal halls described in early Scandinavian legends and sagas. Constructing buildings of this scale required technical knowledge far beyond simple carpentry. Massive roof systems had to support significant loads during harsh Scandinavian winters, and snow accumulation alone could place enormous pressure on timber structures. Modern structural engineers rely on mathematical calculations and computer modeling to predict these forces, but the builders of Gamla Uppsala possessed neither. Yet archaeological evidence suggests that these halls stood for decades and possibly generations. This raises several unanswered questions. How were suitable trees selected? How were load-bearing beams designed? How did builders prevent structural collapse? And how was construction knowledge transmitted without written engineering manuals? The answers remain largely unknown because the buildings themselves have vanished, leaving only post holes and fragments behind. One of the most astonishing discoveries in recent years involved rows of enormous timber posts stretching across the landscape. Archaeologists identified hundreds of post holes, indicating the existence of large wooden pillars that once formed extensive linear structures, and some stretches may have extended for more than a kilometre. The purpose of these posts remains debated. They may have marked ceremonial routes, defined sacred boundaries, symbolized royal authority, or served multiple functions simultaneously. What is certain is the engineering challenge involved. Many of these posts were likely cut from mature trees weighing several tons, and transporting them without modern machinery would have required coordinated labor forces and sophisticated planning. Experimental archaeology has demonstrated that moving and erecting large timber pillars is extraordinarily difficult, even when modern teams possess detailed engineering knowledge. Yet the builders of Gamla Uppsala completed these projects repeatedly. Exactly how they accomplished this remains unclear. Perhaps the least appreciated mystery concerns measurement and planning. Modern aerial surveys reveal that Gamla Uppsala was not a randomly developed settlement. The burial mounds, halls, roads, ritual spaces, and post alignments appear to form an organized ceremonial landscape, and creating such a landscape required accurate surveying. Today, engineers use GPS systems, laser levels, satellite imagery, and digital mapping software. The builders of Gamla Uppsala had none of these tools. Nevertheless, they managed to position structures across large distances with impressive consistency. This mystery resembles challenges found at other ancient sites. The builders of Stonehenge aligned monuments with celestial events. The engineers of the Roman Empire created roads extending thousands of kilometers, and the creators of Machu Picchu organized architecture across difficult mountain terrain. Gamla Uppsala presents a Northern European version of the same puzzle. What surveying methods allowed such precision? No surviving documents provide answers. Engineering is not only about construction, it is also about organization. Many historians believe Gamla Uppsala functioned as a major political and religious center attracting visitors from across Scandinavia. If this interpretation is correct, the logistical implications are enormous. Large gatherings require food supplies, water, transportation systems, storage facilities, and administration. The challenge becomes clearer when compared to later medieval cities. Supporting thousands of temporary visitors demands a complex supply network extending far beyond the settlement itself. Archaeological evidence suggests that Gamla Uppsala occupied a strategic position connected to regional trade routes and fertile agricultural lands. Yet researchers still do not fully understand how such a system operated. The infrastructure that sustained the site has largely disappeared. Unlike Egypt, where stone monuments survive for millennia, Scandinavian societies built primarily with wood. This creates a unique archaeological problem because wood preserves poorly. As a result, much of the technological knowledge behind Gamla Uppsala may have vanished completely. Ancient builders likely understood timber selection, drying methods, structural behavior, joinery techniques, and long-term maintenance. Modern carpenters know that different tree species behave differently under stress, that moisture content affects strength, that grain orientation influences durability, and that joint design determines stability. The people of Gamla Uppsala clearly mastered these principles in practice, yet almost no written evidence survives explaining their methods. Researchers can study the results, but the knowledge itself remains largely lost. Another debate concerns astronomy. Some researchers have proposed that elements of Gamla Uppsala's layout may relate to solar observations or seasonal cycles. Similar theories have been investigated at Stonehenge, Newgrange, Chaco Canyon, and numerous ancient ceremonial centers around the world. Supporters argue that agricultural societies often depended on accurate seasonal knowledge, while critics caution that many proposed alignments may be coincidental. At present, definitive evidence remains elusive. However, if future research confirms intentional astronomical planning, it would reveal another layer of technical sophistication within the site's design. Archaeological lies near the modern town of Monreal de Arisa in Zaragoza province, northeastern Spain. Today, only ruins remain scattered across a strategic hill overlooking the Jalón Valley. Archaeological investigations during the 20th century reveal that beneath the soil existed the remains of a significant Celtiberian settlement that later became a Roman city. Excavations uncovered streets, residential districts, public buildings, water systems, cisterns, and one of the most remarkable discoveries at the site, a Roman bath complex. These findings confirmed that Archaeological was not a simple provincial settlement, but a carefully planned urban centre integrated into the Roman world. Yet, the discoveries also created a series of mysteries that remain only partially understood. Nearly 2,000 years later, archaeologists continue asking how a city built on such difficult terrain could sustain sophisticated infrastructure, manage water supplies, and maintain engineering systems that rival those found in much larger Roman settlements. The first mystery begins with geography itself. Most successful Roman cities were founded near rivers, fertile plains, or major transportation corridors. Archaeological occupied a hilltop position that offered defensive advantages, but created enormous engineering challenges. Building a city on sloping terrain requires solutions for drainage, foundations, transportation, and water management. Modern engineers facing similar conditions rely on surveying instruments, topographic mapping, computer modelling, and advanced construction equipment. The inhabitants of Archaeological possessed none of these technologies, yet archaeological evidence suggests they created a remarkably organised urban environment. Streets followed carefully planned routes, buildings were arranged to maximise available space, and public infrastructure appears integrated into the landscape rather than imposed upon it. Researchers estimate that Roman surveyors could achieve surprising levels of accuracy using instruments such as the groma and chorobates. Experimental archaeology has demonstrated that Roman land surveyors were capable of maintaining alignments over distances exceeding several kilometres, with errors often measured in mere centimetres per 100 metres. But exactly how the planners of Archaeological adapted those techniques to a rugged hilltop environment remains uncertain. The city appears to have been designed according to principles that required precise measurements, yet the methods used to implement those measurements on uneven terrain remain largely invisible. Perhaps no question surrounding Archaeological is more important than water. Every Roman city depended upon reliable water supplies. Water was required for drinking, cooking, sanitation, industrial activities, fountains, and baths. The problem is obvious. Archaeological sits above the surrounding landscape, and gravity naturally favours settlements located below water sources, not above them. Excavations have uncovered cisterns, reservoirs, drainage systems, and hydraulic infrastructure. The existence of these facilities proves that significant quantities of water reach the city. What remains unclear is exactly how. Some researchers suggest that nearby springs may have supplied the settlement. Others believe portions of a water transport network remain undiscovered. Still others propose sophisticated rainwater collection systems. The challenge becomes even greater when considering consumption rates. Studies of Roman bath complexes indicate that even modest baths could consume tens of thousands of litres of water daily, while larger facilities throughout the empire sometimes processed hundreds of thousands of litres. If Archaeological's bath complex operated regularly, the city required a supply system capable of delivering substantial volumes of water continuously. Yet no fully preserved aqueduct has been identified. This creates a technological puzzle. The infrastructure clearly existed, the water clearly arrived, and the engineering system clearly functioned. But key parts of the mechanism remain missing. The discovery of the baths revealed another mystery. Roman baths were among the most technologically advanced structures of the ancient world. They were not simply pools of warm water, but carefully engineered thermal systems. A typical Roman bath included multiple chambers maintained at different temperatures. Visitors moved between cold rooms, warm rooms, and hot rooms, and achieving this required remarkable control over heat transfer. The secret was the hypercaust. This system used elevated floors supported by hundreds of small pillars. Hot air generated by furnaces circulated beneath the floors and through hollow wall spaces, heating entire rooms. Modern studies of reconstructed hypercaust systems have demonstrated interior temperatures exceeding 40 degrees Celsius, and some experiments suggest floor temperatures could approach 50 degrees Celsius directly above heating channels. At Archaeological, archaeologists found evidence that such technology existed, but several questions remain unanswered. How much fuel was required to maintain operation? How many workers managed the furnaces? How was airflow regulated? How did engineers prevent structural damage caused by repeated heating and cooling cycles? Even modern engineers recognize that thermal management is a complex challenge. Materials expand and contract, heat distributes unevenly, and moisture affects durability. Roman builders solved these problems with remarkable success, yet the technical knowledge behind their solutions was almost entirely lost. Archaeological experienced significant seasonal temperature variations. Summers in northeastern Spain can be extremely hot, while winters can become surprisingly cold. This environmental challenge may explain another engineering mystery. Many Roman buildings appear designed to regulate indoor temperatures naturally. Archaeological evidence suggests thick masonry walls, strategic building orientation, and carefully designed ventilation systems may have contributed to passive climate control. Modern sustainable architecture often relies upon similar principles. Thermal mass stores heat during the day and releases it gradually at night. Air circulation improves comfort without mechanical systems, and building orientation influences solar exposure. What makes Archaeological fascinating is that these principles may have been applied nearly 2,000 years ago. Because upper sections of most structures have disappeared, researchers cannot fully reconstruct the original designs. As a result, the extent of Roman climate engineering remains a subject of ongoing investigation. Every stone visible at Archaeological raises another question. How did it get there? Many construction materials had to be transported uphill. Large stone blocks required extraction, shaping, transportation and placement. Even with modern equipment, moving heavy stone over uneven terrain is challenging. The Romans accomplished such tasks throughout the empire. At sites like the Colosseum, engineers transported stones weighing several tons, while at Baalbek, Roman builders worked with blocks exceeding 800 tons. Archaeological operated on a smaller scale, but the logistical principles remain impressive. Researchers estimate that a single large construction project could require thousands of individual transport operations. Draft animals, wooden sledges, rollers, cranes, and human labor likely played essential roles. However, very little direct evidence survives regarding the specific construction techniques used at Archaeological. The buildings survive, but the machines do not. Perhaps the most overlooked mystery is surveying. Before any building could be constructed, engineers had to understand the landscape. Modern surveyors use GPS satellites capable of determining positions within centimeters, while Roman surveyors relied upon geometry, observation, and experience. Yet archaeological evidence throughout the Roman Empire demonstrates astonishing accuracy. Roads maintained straight alignments over vast distances. Aqueducts preserved gradients measured in centimeters per kilometer, and urban layouts followed carefully organized plans. Archaeological was part of this tradition. Its streets, infrastructure, and public spaces indicate systematic planning rather than random growth. But no engineering manuals from Archaeological survive. No blueprints exist. No project reports explain how measurements were taken. Only the results remain. What do you think? Did the engineers of Archaeological possess practical techniques that have been completely lost to history? Or will future discoveries eventually reveal the secrets behind this remarkable hilltop city? Let us know your thoughts in the comments below. Avaldsnes sits on Karmøy Island on the western coast of Norway overlooking the narrow Karmsundet Strait. Archaeological investigations began in the 19th century, but major excavations during the 20th and 21st centuries transformed understanding of the site. Beneath medieval structures and royal estates, archaeologists uncovered evidence of elite Viking settlements, monumental halls, harbours, workshops, burial sites, and centuries of continuous occupation. The discoveries revealed that Avaldsnes was not simply a village. It was one of the most important centres of power in Viking Age Scandinavia. What makes Avaldsnes remarkable is not only its historical importance, but also the possibility that the site functioned as a technological and logistical hub, whose capabilities still challenge modern understanding of Viking engineering. The first mystery begins with geography. Avaldsnes occupies an almost impossibly strategic location. The settlement overlooks Karmsundet, a narrow shipping corridor that stretches along Norway's western coastline. During the Viking Age, this strait served as one of the safest routes for ships travelling between northern and southern Scandinavia. At certain points, the channel narrows to only a few hundred metres, meaning any vessel moving through the region would have been visible from Avaldsnes. Modern geographic analysis suggests that few locations along the Norwegian coast provide such complete control over maritime traffic. The position allowed rulers to monitor trade, collect taxes, regulate movement, and project military power across enormous distances. The mystery is how Viking leaders identified this location so precisely. Today, strategic maritime planning involves satellite imagery, topographic surveys, and geographic information systems. Yet more than 1,000 years ago, the founders of Avaldsnes selected a position that maximized visibility, accessibility, and control with extraordinary efficiency. Was this merely experience accumulated over generations? Or did Viking navigators possess sophisticated surveying methods that archaeology has yet to identify? Excavations have revealed traces of enormous Viking longhouses associated with elite rulers. Some structures exceeded 40 metres in length. For comparison, many ordinary Viking houses measured less than 15 metres. These halls were among the largest wooden buildings constructed in Northern Europe during their time. Building on such a scale created significant engineering challenges. Western Norway experiences powerful Atlantic storms, strong winds, heavy rainfall, and seasonal snow loads. A roof spanning dozens of meters required careful load distribution and structural stability. Unlike modern architects, Viking builders had no steel reinforcements, no concrete foundations, and no engineering software. Yet many of these structures remained functional for generations. Experimental archaeologists attempting to reconstruct Viking halls have discovered that even minor mistakes in pillar placement can destabilize entire roof systems. The fact that the original halls survived suggests their builders understood complex structural principles. The mystery is that no written construction manuals survive. The halls demonstrate advanced practical engineering, but the knowledge behind their design appears to have disappeared. Perhaps no mystery surrounding Avaldsnes is more significant than its connection to Viking ships. The power of Avaldsnes depended entirely upon control of maritime routes. Such control required fleets capable of moving warriors, goods, livestock and resources across thousands of kilometers of coastline. The Viking longship remains one of the most efficient wooden vessels ever built. Archaeological evidence from famous ships such as the Oseberg ship and Gokstad ship demonstrates astonishing technical sophistication. Their clinker-built hulls combined flexibility with strength, while their shallow drafts allowed navigation of rivers and survival during open ocean voyages. Modern naval architects studying reconstructed Viking ships have repeatedly noted how effective their designs are. Computer simulations suggest that some longships achieve speeds exceeding 15 knots under favourable conditions, and certain replicas have demonstrated remarkable seaworthiness in North Atlantic waters. Yet a fundamental mystery remains. How did Viking shipbuilders determine the optimal hull shapes? Modern vessel design relies heavily on hydrodynamic calculations, fluid modelling and extensive testing, but Viking builders had none of these tools. Some researchers believe the designs evolved purely through trial and error, while others argue that generations of accumulated engineering knowledge may have formed a sophisticated but unwritten system of design rules. If such a system existed, Avaldsnes would likely have been one of its most important centres. Avaldsnes stood at the centre of a maritime network extending from Scandinavia to Iceland, Greenland and North America. These voyages required extraordinary navigational abilities. The distance from Norway to Iceland exceeds 900 kilometres, and Greenland lies even farther west. Successful crossings demanded accurate orientation over vast stretches of ocean, where land remained invisible for days. One of the most debated mysteries involves the legendary Viking sunstone. Several medieval texts describe special stones capable of locating the sun even under cloudy conditions. Modern experiments using Iceland spar, a transparent calcite crystal, have shown that polarized sunlight can indeed reveal the sun's position when hidden by clouds. The results surprised many researchers. Laboratory studies demonstrated that the technique could potentially improve navigation accuracy significantly in northern latitudes where weather conditions are often poor. However, direct archaeological evidence remains limited. Did Viking navigators actually use such technology? Or are modern researchers projecting scientific explanations onto medieval legends? Avaldsnes, as a centre of royal maritime activity, would have been one of the most likely places for such navigational knowledge to develop and spread. Another mystery involves the broader landscape surrounding Avaldsnes. The region contains burial mounds, standing stones, monuments, ancient roads and ceremonial sites arranged across the terrain. Many appear positioned with remarkable intentionality. Some researchers suggest that these features may have served practical functions in addition to religious or political roles. Large monuments could have acted as navigation markers visible from ships approaching the coastline, while certain elevated positions provided long-distance sightlines across the strait. If correct, the landscape itself may have functioned as a form of infrastructure. Long before lighthouses appeared, Viking sailors may have relied on carefully placed landmarks integrated into the environment. This possibility raises important questions. Who designed these systems? How were locations selected? And how was knowledge of their purpose transmitted across generations? The answers remain uncertain. Avaldsnes also reveals evidence of iron production and metalworking. To modern observers, ancient ironworking may seem relatively simple, but in reality producing usable iron is an extraordinarily complex process. Bloomery furnaces must reach temperatures approaching 1,200 degrees Celsius, and operators must control airflow, fuel quality, furnace dimensions and ore composition with remarkable precision. Even small errors can dramatically reduce efficiency. Archaeological remains suggest that Viking smiths repeatedly achieved successful production on a large scale. The mystery is how. Without thermometers, pressure gauges or modern measuring equipment, ancient metalworkers somehow optimized systems that modern experimental archaeologists often struggle to reproduce. Many reconstructed furnaces fail repeatedly before achieving results comparable to archaeological examples. This suggests that Viking metallurgists possessed practical knowledge far more sophisticated than surviving evidence can fully explain. Perhaps the most overlooked mystery concerns administration. Avaldsnes functioned as a royal centre connected to territories spread across enormous distances. Maintaining authority required communication. Orders had to travel, taxes had to be collected, military forces had to be mobilised, and trade had to be regulated. Today, such tasks depend on telecommunications, roads, and digital systems, yet Viking rulers possessed none of these advantages. Historical sources nevertheless indicate that they successfully coordinated activities across large portions of Scandinavia. Some researchers propose networks of signal fires, relay stations, and maritime communication routes, while others believe personal relationships and decentralized governance played a larger role. Regardless of the explanation, the logistical achievement remains extraordinary. What do you think? Were the achievements of Avaldsnes simply the result of generations of experience? Or did the Vikings possess engineering and navigational knowledge that has been largely lost to history? Let us know your thoughts in the comments below. At the centre of Rome, Italy, rising approximately 40 metres above the Roman Forum, stands Palatine Hill, one of the most famous archaeological sites in the world. According to Roman tradition, this was the place where Romulus founded Rome in 753 BC. Archaeological investigations began as early as the Renaissance, but major scientific excavations accelerated during the 19th and 20th centuries. What researchers expected to find were the remains of imperial palaces. What they discovered instead was something far more intriguing: evidence of enormous engineering systems hidden beneath centuries of ruins. Today, archaeologists estimate that the imperial complexes covering Palatine Hill once occupied more than 150,000 square meters. Beneath the visible ruins lies a labyrinth of tunnels, foundations, reservoirs, drainage networks, and structural systems that continue to challenge modern understanding of ancient engineering. Most ancient capitals were constructed on relatively stable terrain, but Palatine Hill presented a completely different challenge. Its slopes were irregular, its geology varied from one section to another, and large portions required extensive modification before major construction could begin. Yet Roman emperors transformed the hill into the political centre of the empire. Massive complexes such as the Domus Flavia, Domus Augustana, and later imperial palaces stretched across the summit. Modern engineers understand the difficulty of constructing large buildings on uneven terrain because every structure generates pressure on the ground beneath it, and the larger the structure, the greater the risk of settlement, cracking, or collapse. Some walls on Palatine Hill still stand nearly 20 meters high after almost 2,000 years. Even more remarkable, many of the supporting foundations remain structurally stable despite centuries of earthquakes, erosion, and human activity. The mystery is not that the Romans built these structures, but how they calculated the necessary support systems without modern geology, structural analysis software, or advanced surveying equipment. One of the greatest surprises uncovered by archaeologists was the scale of the underground infrastructure. Beneath the palaces lies a vast network of corridors, service passages, storage chambers, drainage systems, and structural galleries. Some tunnels extend for hundreds of meters beneath buildings weighing thousands of tons. In modern architecture, underground construction beneath large structures requires extensive calculations regarding load distribution, ventilation, groundwater control, and long-term stability. The Romans somehow achieved these objectives nearly 2 millennia ago. Researchers continue to debate the original purpose of many underground passages. Some appear to have been used by servants, others likely transported supplies, and certain sections may have functioned as maintenance corridors for water systems and utilities. Yet, significant portions remain poorly understood, and the complete engineering logic of the underground network has never been fully reconstructed. Summer temperatures in Rome regularly exceed 35 degrees Celsius, making the maintenance of comfortable living conditions inside enormous stone structures a major challenge. Evidence from Palatine Hill suggests that Roman architects employed sophisticated passive cooling techniques. Thick walls absorbed heat during the day and released it slowly at night. Courtyards created airflow patterns that encouraged natural ventilation. Water channels running through certain areas may have contributed to cooling effects, while underground chambers likely helped regulate temperature fluctuations. Modern sustainable architecture increasingly employs similar principles. Buildings designed for energy efficiency often rely on thermal mass, natural airflow, and evaporative cooling rather than mechanical air conditioning. This remarkable similarity raises an important question. Did Roman architects gradually discover these principles through centuries of experimentation, or did they possess a more systematic understanding of environmental engineering than historians currently recognize? Perhaps no technological mystery on Palatine Hill is more famous than Roman concrete. Many structures on the hill contain concrete mixtures that have survived for nearly 2,000 years. Some sections remain stronger than many modern equivalents, despite constant exposure to weather and environmental stress. Scientific studies have revealed complex combinations of lime, volcanic ash, aggregate, and mineral reactions occurring over long periods. Recent research suggests that certain Roman concrete formulations may possess self-healing properties, with tiny cracks triggering chemical reactions that gradually seal damaged areas. For comparison, many modern reinforced concrete structures are designed for service lives of roughly 50 to 100 years before major repairs become necessary. Palatine Hill demonstrates durability on a completely different scale. Scientists can identify the ingredients and analyze the chemistry, yet many aspects of the manufacturing process remain uncertain. The exact methods used by Roman builders continue to generate debate among material scientists worldwide. Water was essential for imperial life. The palaces required drinking water, fountains, baths, kitchens, gardens, and sanitation systems, yet Palatine Hill stood above much of the surrounding city. Archaeological excavations have revealed extensive hydraulic infrastructure, including reservoirs, lead pipes, channels, distribution systems, and storage facilities. The challenge was maintaining reliable water delivery across varying elevations. Modern water networks rely heavily on pumps, pressure controls, and monitoring systems, technologies that Roman engineers lacked. Nevertheless, they successfully supplied vast quantities of water to the imperial complex. Researchers still debate the exact operation of several hydraulic components. Some pipe networks appear more sophisticated than expected, while certain reservoirs may have served multiple engineering functions simultaneously. Even after decades of investigation, a complete understanding of the water management system remains elusive. Many of the surviving structures on Palatine Hill showcase Roman mastery of arches and vaults. These curved architectural forms allowed builders to create enormous interior spaces while reducing dependence on dense forests of support columns. The engineering challenge is significant because every arch must distribute forces correctly, and every vault must channel weight toward carefully positioned supports. Small errors can trigger catastrophic failure, yet many Roman vaults have survived earthquakes, fires, invasions, and centuries of neglect. Some structures continue to stand despite the loss of large sections of supporting material. Modern engineers can model these systems using advanced software, but Roman builders achieved similar results through methods that remain only partially understood. Before construction could begin, the Romans had to measure the terrain. This seemingly simple task may represent one of the greatest mysteries of all. Building complexes covering tens of thousands of square meters required accurate alignment, elevation measurements, drainage planning, and structural positioning. Today, such tasks are performed using GPS systems, laser scanners, digital mapping equipment, and computer-generated models. Roman engineers possessed none of these technologies. Yet archaeological surveys repeatedly reveal extraordinary precision throughout the Palatine complexes. Walls align correctly, drainage gradients function efficiently, and structural relationships remain remarkably consistent. The instruments used by Roman surveyors are known in general terms, but the level of precision they achieved remains difficult to explain fully. Among the most intriguing discoveries on Palatine Hill are the remains of the Domus Transitoria, the first grand palace associated with Emperor Nero. Although much of the structure was destroyed during the Great Fire of AD 64, excavations revealed evidence of remarkable engineering sophistication. The palace featured marble decorations from distant provinces, advanced water features, carefully designed lighting effects, and elaborate interior spaces intended to manipulate perception and movement. Some researchers believe the palace incorporated combinations of water, reflection, architecture, and natural light to create immersive visual experiences unlike anything previously seen in Rome. Unfortunately, much of the structure vanished before detailed documentation could survive. The surviving remains hint at technological capabilities that historians can only partially reconstruct. Standing beside the ancient Aurelian walls is one of the strangest monuments in the entire Roman world. It is not a temple, it is not an amphitheatre, and it is not a triumphal arch. It is a pyramid. Known as the Pyramid of Cestius, the structure rises approximately 36.4 meters, 119 feet high, with a base measuring about 29.5 meters, 97 feet on each side. Built around 1812 BC as the tomb of the Roman magistrate Gaius Cestius, it remains one of the best preserved monuments from ancient Rome. Its existence alone raises questions. Why would Romans, famous for arches, domes, roads, and aqueducts, suddenly construct an Egyptian-style pyramid in the heart of Italy? Yet the deeper archaeologists investigate, the more extraordinary mysteries emerge, not merely about its purpose, but about the engineering knowledge required to build it. An inscription on the monument reveals a remarkable detail. The pyramid was completed in just 330 days. At first glance, this may not sound extraordinary, but consider what the project involved. Workers had to prepare foundations, construct a massive concrete core, produce enormous quantities of brickwork, transport marble from distant quarries, shape the exterior, decorate the burial chamber, and complete all finishing work within less than a year. Modern engineering studies estimate that the structure contains thousands of tons of construction material. For comparison, many modern public buildings of similar size often require significantly longer construction schedules, despite cranes, trucks, power tools, and computer planning systems. Ancient Roman builders possessed none of these advantages. How they organized labor, coordinated material deliveries, and maintained such speed remains poorly understood. Some historians estimate that hundreds of workers may have operated simultaneously. Others suggest that the Roman Empire's logistical systems were so efficient that materials could move through supply networks with a speed rarely associated with ancient civilizations. Whatever the explanation, the construction schedule remains one of the most astonishing aspects of the monument. The Pyramid of Cestius appears Egyptian on the outside. Inside, however, it is entirely Roman. Unlike the Great Pyramid of Giza, which consists of millions of limestone blocks, the Pyramid of Cestius relies primarily on a concrete core covered with brick and marble. This concrete, known as opus caementicium, continues to fascinate scientists today. Modern laboratory studies have revealed that Roman concrete often contains volcanic ash, lime, and mineral compounds capable of producing self-healing reactions when cracks develop. Researchers studying Roman harbour structures have discovered examples that remained durable for nearly 2,000 years despite constant exposure to seawater. The Pyramid of Cestius demonstrates a similar level of durability. For over 2,000 years it has survived earthquakes, storms, pollution, urban expansion, military conflicts, and environmental degradation. Many modern concrete structures begin showing major deterioration after only 50 to 100 years. The Pyramid of Cestius continues standing after 20 centuries. Scientists can identify many of the ingredients used by Roman builders. What remains unclear is whether the Romans fully understood the long-term chemical reactions occurring inside their concrete, or whether they achieved these results through generations of practical experimentation. Either possibility suggests a level of material science far more sophisticated than commonly assumed. The pyramid's steep sides rise at angles far sharper than most Egyptian pyramids. Maintaining symmetry over a height exceeding 36 meters required extraordinary precision. Today, engineers use laser levels, GPS systems, digital surveying equipment, and computer modeling. Roman builders relied on ropes, plumb bobs, measuring rods, and geometry. Yet modern surveys reveal remarkably accurate alignment and symmetry. This raises a fundamental question. How much mathematical knowledge did Roman surveyors possess? Roman engineers are known to have mastered land surveying techniques. They designed roads crossing entire continents, aqueducts maintaining gradients of only a few centimeters per kilometer, and military camps with highly standardized layouts. The Pyramid of Cestius may represent another example of lost practical knowledge. The structure suggests a sophisticated understanding of geometry and construction control, yet very little technical documentation survives explaining exactly how such precision was achieved. One of the most overlooked mysteries involves the monument's white marble exterior. The entire structure was originally covered with fine Carrara marble. This stone originated hundreds of kilometers away in northern Italy. Extracting the marble required quarrying operations. Transporting it required roads, rivers, ships, carts, workers, animals, and administrative coordination. Every block had to arrive at the correct location and at the correct stage of construction. The logistics become even more impressive when viewed within the 330-day construction deadline. For comparison, the construction of Egyptian pyramids required enormous transportation systems. The builders of the Parthenon in Athens faced similar challenges. The Roman Empire appears to have developed an equally sophisticated supply network. Yet historians still debate the true scale of Roman construction logistics because the documentation is fragmentary. The Pyramid of Cestius may represent only a tiny surviving example of a system far larger than archaeologists can currently reconstruct. Within the monument lies a small burial chamber measuring approximately 5.95 meters long, 4.10 meters wide, and 4.80 meters high. The chamber contains delicate frescoes painted on white backgrounds. Its size presents an interesting contradiction. An enormous pyramid surrounds a relatively modest burial room. This raises questions about symbolism. Was the pyramid intended primarily as a tomb? Or was it also a public statement of wealth, power, political status, and cultural influence? Many details of the original interior remain unknown because grave robbers likely entered the structure centuries ago. Artifacts that might have explained the owner's intentions are largely missing. The surviving chamber therefore preserves only fragments of the monument's original story. Perhaps the greatest historical mystery concerns the design itself. The pyramid was built shortly after Rome's conquest of Egypt in 30 BC. Egyptian culture suddenly became fashionable among Roman elites. Obelisks appeared throughout Rome. Egyptian religious practices gained followers. Artistic styles spread across the empire. Yet the Pyramid of Cestius remains unique. Romans constructed countless tombs, but almost none adopted such an extreme Egyptian form. Why did Gaius Cestius choose a pyramid instead of a traditional Roman mausoleum? Some scholars suggest it reflected admiration for Egypt. Others believe it symbolized prestige and international influence. Still others argue that the shape carried religious meanings now lost to history. The absence of written explanations means the true motivation remains uncertain. The monument's continued survival presents another puzzle. Over 2,000 years, Rome experienced invasions, civil wars, earthquakes, economic collapse, medieval rebuilding, and modern urban development. Many ancient structures vanished completely. The Pyramid of Cestius endured. Its survival was partly accidental. During the construction of the Aurelian walls in the 3rd century AD, the pyramid was incorporated into Rome's defensive system. This decision protected the structure from destruction. Yet preservation alone does not explain its durability. The monument still depends on engineering decisions made more than 20 centuries ago. The foundations continue supporting immense weight. The concrete remains stable. The geometry remains intact. Every surviving feature points toward a level of practical engineering expertise that historians can observe but not fully reconstruct. Perched on a strategic hill overlooking the confluence of the Mtukvari and Aragvi rivers near modern Mtsketa, Georgia, approximately 20 kilometers northwest of Tbilisi, Armazi was one of the most important centers of the ancient kingdom of Iberia. The site was first identified through historical records and archaeological investigations conducted throughout the 20th century. Excavations revealed the remains of a fortified royal city that served as one of the political and religious centers of the powerful Caucasian state that flourished between Rome and Persia. At first glance, Armazi appears to be just another ruined fortress. Yet beneath its collapsed walls lies evidence of engineering knowledge that continues to puzzle archaeologists today. The city occupied one of the most strategically important locations in the Caucasus, controlling trade routes that connected Europe, Asia, and the Middle East. More importantly, its builders solved a series of technological challenges that remain only partially understood nearly 2,000 years later. Armazi occupied a naturally defensive position atop a steep rocky hill. From its summit, observers could monitor movement along major river valleys stretching for dozens of kilometers. Such a location provided military advantages, but it also created enormous engineering problems. Every stone block, every construction material, every food supply, and every drop of water had to be transported uphill. Modern engineers understand how difficult such logistics become even with machinery. Yet Armazi's builders accomplished this on a large scale using only ancient technology. The challenge becomes even more impressive when compared with other hilltop centers of the ancient world. The builders of Machu Picchu in Peru faced similar transportation problems. The craters of Masada in Israel encountered comparable logistical obstacles. Yet Armazi emerged centuries earlier as one of the Caucasus region's most important political centers. The question is simple. How did its builders manage such a complex construction project with the technological resources available at the time? One of the most fascinating mysteries of Armazi involves its defensive walls. Excavations reveal massive fortification systems built from carefully fitted stone blocks. Some sections display construction techniques resembling those used throughout the Roman world. Others appear closer to Persian traditions. Still others contain local innovations unlike either major civilization. This hybrid engineering approach creates a puzzle. Armazi's builders were not merely copying foreign methods, They were selectively combining technologies from multiple cultures and adapting them to local conditions. Some surviving wall segments demonstrate remarkable durability, despite nearly 2 millennia of earthquakes, weathering, warfare, and abandonment. Geological studies show that eastern Georgia experiences significant seismic activity, yet portions of the fortification survived long after many younger structures disappeared. Researchers continue debating whether the builders intentionally incorporated earthquake-resistant design principles or whether the resilience emerged accidentally through experience and experimentation. Without surviving engineering manuals, the answer remains unknown. The Caucasus Mountains sit within one of the world's most complex tectonic regions. The Arabian and Eurasian plates continue interacting beneath the landscape, generating frequent seismic activity. This creates a major mystery. Ancient builders had no seismographs, no geological models, and lacked modern structural analysis software. Yet, some of Almazy's surviving foundations exhibit characteristics that engineers often associate with seismic resilience. Several wall systems appear designed to distribute loads across wider surfaces. Certain stone blocks show evidence of carefully controlled placement rather than random stacking. In some areas, the builders seem to have prioritized flexibility over rigidity. Modern earthquake engineering frequently relies upon allowing structures to absorb movement, rather than resisting it completely. Could Almazy's architects have discovered similar principles through centuries of observation? No written evidence survives to confirm the theory, but the physical remains continue raising questions. Perhaps the most overlooked mystery involves transportation. The construction of Almazy required enormous quantities of stone. Archaeologists estimate that thousands of tons of material were moved during various construction phases. Even today, transporting such weight uphill would require significant planning. Ancient engineers faced additional obstacles. No diesel engines, no hydraulic cranes, no steel cables, and no modern roads. Yet massive blocks somehow reach the summit. The same mystery appears at many famous archaeological sites. The builders of Baalbek transported stone blocks weighing hundreds of tons. The craters of Stonehenge moved stones across vast distances. The engineers of the Egyptian pyramids relocated millions of limestone blocks. Almazy belongs to this broader category of ancient logistical puzzles. Researchers suspect combinations of ramps, rollers, sledges, manpower, and animal power were involved. However, direct evidence remains surprisingly scarce. The exact methods have vanished, but the results remain. A fortress without water is not a fortress. This reality creates one of Almazy's most intriguing engineering mysteries. The city stood high above nearby rivers. During peacetime, transporting water uphill would have been difficult. During warfare, dependence on external water sources could prove catastrophic. Excavations uncovered reservoirs, channels, storage facilities, and hydraulic infrastructure, suggesting sophisticated water management. The problem is that archaeologists still do not fully understand how the entire system functioned. How was water collected? How much could be stored? How long could the city survive under siege? Modern military historians note that water logistics often determine the fate of ancient fortresses. A city capable of storing hundreds of thousands of litres gained a major strategic advantage. Some researchers believe Almazy's water systems were considerably more advanced than surviving remains suggest. If true, much of the infrastructure may still lie buried beneath the site. Archaeological investigations revealed extensive palace structures within Almazy. The foundations indicate large ceremonial and administrative buildings. These structures required careful planning, load distribution, and architectural coordination. Today, engineers use advanced calculations to determine structural stability. Ancient builders did not, or at least They lacked our mathematical tools, yet they repeatedly constructed buildings that remained standing for centuries. This pattern appears across the ancient world. Roman engineers built the Pantheon with its 43-meter dome. Egyptian builders erected pyramids containing millions of stone blocks. The architects of Petra carved entire monuments into solid rock. Amazi's builders operated on a smaller scale but confronted many of the same engineering challenges. The knowledge required clearly existed, but the documentation largely disappeared. The Kingdom of Iberia occupied a region rich in mineral resources. Archaeological discoveries throughout Georgia demonstrate extensive metalworking traditions dating back thousands of years. Iron tools, weapons, and production evidence suggest sophisticated metallurgical expertise. Producing iron is far more difficult than most people realize. Furnaces must exceed temperatures approaching 1,200 degrees Celsius. Airflow must be carefully regulated. Fuel quality must remain consistent. Ore composition must be understood. Even slight errors can ruin an entire production cycle. Experimental archaeologists attempting to recreate ancient furnaces frequently discover that seemingly simple systems conceal surprisingly advanced engineering principles. The craftsmen of Amazi almost certainly possessed practical knowledge of heat management, combustion dynamics, and material behavior. Yet virtually none of their technical instructions survive. Like many ancient technologies, the products remain while the knowledge behind them vanished. One of the most important discoveries associated with the site involves inscriptions written in the so-called Amazi script. These texts reveal evidence of administration, governance, diplomacy, and political organization. This creates another mystery. Complex states require information systems, taxation requires records, construction projects require coordination, military operations require communication, trade requires accounting. Amazi clearly possessed these capabilities, yet only fragments survive. It is possible that thousands of documents once existed within the kingdom. Most were likely written on perishable materials that disappeared centuries ago. If those records survived, they might answer many of the engineering questions surrounding the city. Instead, archaeologists are left reconstructing the past from scattered clues. In 1926, during Benito Mussolini's massive urban redevelopment projects, workers demolishing old buildings in the heart of Rome unexpectedly uncovered something hidden beneath the modern city. As excavation continued, archaeologists revealed 4 ancient Republican temples, sections of paved streets, monumental foundations, and parts of the massive Theatre of Pompey complex. The site became known as Lago di Torre Argentina. At first glance, the ruins appeared to be another collection of Roman remains. But decades of excavation would reveal something far more intriguing. Beneath the crowded streets of modern Rome lay evidence of engineering capabilities that continue to challenge archaeologists and structural experts today. The temples date from approximately the 4th to the 2nd centuries BCE, meaning some structures have survived for more than 2,200 years. Yet many of the technologies that made such survival possible remain only partially understood. One of the greatest engineering puzzles begins with the location itself. Lago di Torre Argentina sits within the ancient floodplain of the Tiber River. Modern engineers recognize floodplains as some of the most difficult environments for large-scale construction. Soft sediments, seasonal flooding, groundwater fluctuations, and long-term soil movement create serious structural risks. Even today, projects built on similar terrain often require deep foundation systems, reinforced concrete piles, soil stabilization techniques, and continuous monitoring. Yet Roman builders erected monumental stone temples, weighing thousands of tons on this challenging landscape over 2 millennia ago. Archaeological investigations reveal massive foundation platforms extending deep below the visible ruins. These foundations distributed enormous loads across unstable ground with remarkable effectiveness. The mystery is not simply that the structures were built. The mystery is how Roman engineers determined where and how deep to build without geological surveys, drilling equipment, computer modeling, or modern soil analysis. The survival of these foundations through centuries of floods, earthquakes, urban development, and environmental change suggests a level of practical geotechnical knowledge that remains difficult to fully reconstruct. For comparison, many medieval structures built more than 1,000 years later suffered severe settlement problems. Yet portions of the foundations at Largo di Torre Argentina remain remarkably stable. Beneath the temples lies one of the most famous yet least understood technologies of the ancient world, Roman concrete. Known as opus caementicium, this material formed the backbone of Roman engineering. Samples recovered from structures throughout Rome demonstrate extraordinary durability. Modern concrete often begins showing significant deterioration after 50 to 100 years, particularly when exposed to moisture and environmental stress. The concrete used in Largo di Torre Argentina has survived more than 2,000 years. Scientific analysis has identified several key ingredients: volcanic ash known as pozzolana, lime, stone aggregates, and water. Yet knowing the ingredients is not the same as understanding the technology. Recent materials science research has shown that some Roman concrete contains microscopic lime clasts, capable of promoting self-healing reactions when cracks develop. These reactions can generate new mineral growth that helps seal damage. The question is whether Roman builders intentionally engineered these properties or accidentally discovered them through centuries of experimentation. No surviving technical manuals explain the process. No engineering documents reveal quality control procedures. No written instructions describe how mixtures were optimized for different construction environments. The concrete remains, but the knowledge behind it largely disappeared. Water was both Rome's greatest resource and one of its greatest threats. The Tiber River provided transportation, trade routes, and fresh water, but it also flooded frequently. Historical records indicate numerous major floods throughout Roman history. Some inundated large sections of the city. Yet the temples of Largo di Torre Argentina remained functional for centuries. Excavations have revealed evidence of sophisticated drainage systems beneath the site, including channels, stone-lined conduits, elevated platforms, and engineered surfaces designed to redirect water flow. However, only fragments survive. Much of the original hydraulic network has either been destroyed, buried beneath later construction, or remains inaccessible beneath modern Rome. This creates a fascinating problem. Archaeologists can see the results, but they cannot see the entire system. Computer reconstructions suggest that Roman engineers may have integrated the temple complex into a broader urban drainage network connected to roads, sewers, and nearby public infrastructure. If true, the site represents part of a citywide hydraulic machine operating at a scale comparable to some modern municipal systems. Yet significant portions remain hidden beneath the modern city, leaving many questions unanswered. The temples discovered at Largo di Torre Argentina were not constructed at the same time. Some were separated by centuries. Different governments, different architects, different political periods, and different construction teams contributed to the complex. Despite this, modern laser surveys reveal impressive geometric consistency. Walls align with extraordinary precision. Foundation platforms maintain carefully controlled orientations. Structural elements exhibit accuracy that often differs by only centimeters across distances of dozens of meters. Today, such precision is routinely achieved using GPS systems, laser scanners, electronic total stations, and computer-assisted design software. Roman engineers possessed none of these technologies. Their primary surveying instrument was the groma, a relatively simple device consisting of crossed arms and hanging plumb lines. The question is not whether the groma worked. The question is how such apparently simple tools achieved results that continue to impress modern surveyors. Some researchers argue that Roman surveying techniques have been underestimated. Others suggest that generations of accumulated practical experience created levels of accuracy that written sources fail to capture. Whatever the explanation, the precision remains remarkable. Every visible ruin at Lago di Torre Argentina represents a transportation challenge. Columns weighing multiple tons had to be quarried, transported, positioned, and aligned. Stone blocks were moved through crowded urban environments without trucks, cranes, hydraulic lifts, or powered machinery. Experimental archaeology has demonstrated that Roman lifting devices were capable of extraordinary performance. Reconstructions of Roman treadwheel cranes indicate lifting capacities ranging from several tons to more than 6 tons under ideal conditions. Yet many questions remain. How are operations coordinated? How many workers participated? How are loads stabilized? How are precision placements achieved without modern measuring equipment? The problem becomes even more impressive when considering the scale of Roman construction elsewhere. The same civilization that built the temples of Largo di Torre Argentina also constructed the Pantheon, aqueducts spanning dozens of kilometers, and amphitheaters capable of holding tens of thousands of spectators. The technologies clearly worked, but the details of their operation remain incomplete. Adjacent to the temple complex once stood one of the greatest structures in Republican Rome, the Theatre of Pompey. Completed around 55 BCE, it was the first permanent stone theatre ever built in Rome. Ancient sources estimate a capacity between 15,000 and 20,000 spectators. Today, only fragments survive beneath modern buildings. This creates an extraordinary archaeological mystery. Ancient writers described the theatre. Excavations reveal portions of its foundations. Modern technology can map buried remains. Yet no complete architectural plans survive. No engineering reports exist. No construction manuals explain how the project was organized. The building represented one of the largest construction undertakings of its era. Yet much of the technical knowledge required to create it vanished with the Roman world. Ironically, modern researchers often understand the final structure better than the engineering process that produced it. Saganagui, hidden within the limestone mountains of the Gobi Altai region of southern Mongolia, does not resemble the pyramids of Egypt, the temples of Mesopotamia, or the stone circles of Europe. There are no towering monuments, no carved inscriptions, and no massive walls. Yet this cave contains one of the most important records of human technological evolution ever discovered in Central Asia. Archaeological evidence suggests that humans repeatedly occupied the cave between approximately 70,000 and 40,000 years ago, during one of the most critical periods in human history, the transition from archaic populations to fully modern humans. What makes Saganagui extraordinary is not its size, but the technological sophistication hidden within thousands of stone tools found beneath its floor. These artifacts reveal engineering principles, manufacturing techniques, and knowledge transmission systems that remain only partially understood today. Located in the Gobi Altai Mountains of southwestern Mongolia, Saganagui, meaning White Cave, was first documented by researchers during Soviet Mongolian archaeological investigations in the 20th century. Systematic excavations later revealed deep cultural layers containing stone tools, animal remains, charcoal, and evidence of repeated human occupation. Radiometric dating and stratigraphic analysis demonstrated that the cave preserved one of the longest Paleolithic sequences in Mongolia, spanning tens of thousands of years. What initially appeared to be a simple prehistoric shelter soon emerged as a rare technological archive from an era when humanity was developing some of its most advanced Stone Age innovations. Among the most significant discoveries at Sarganagui are tools produced using the level-way technique. To modern observers, these stone flakes may seem primitive. In reality, Levallois technology represents one of the earliest known examples of advanced manufacturing planning. Unlike simple stone knapping, Levallois production required craftsmen to shape a stone core through multiple preparatory stages before striking off a final flake with a predetermined shape. Researchers often compare the process to manufacturing a component from a mold. The desired product existed first in the maker's mind long before the final strike occurred. Experimental archaeology has demonstrated that mastering Levallois technology requires extensive training, and a single mistake can destroy hours of preparation. What remains unclear is how such sophisticated knowledge developed. The cave contains evidence that these techniques were practiced repeatedly over thousands of years, suggesting the existence of highly effective systems of education and skill transmission. Yet no written language existed, no diagrams existed, and no manuals survived. How could technological knowledge requiring such precision be passed accurately from generation to generation for tens of thousands of years? The question remains unanswered. One of the most surprising discoveries at Sarganagui is the consistency of many stone tools. When archaeologists measure flakes produced from Levallois cores, they often find recurring patterns in shape, thickness, and dimensions. Such standardization is not accidental. In modern manufacturing, consistency usually results from measurement systems, templates, or quality control procedures. The people of Sarganagui possessed none of these, yet many artifacts display a level of repeatability that suggests craftsmen were following highly structured production methods. This creates a fascinating mystery. How did prehistoric toolmakers maintain manufacturing standards without rulers, written instructions, or numerical systems? Some researchers suggest that apprentices learned through years of direct observation, while others argue that cognitive abilities among these populations may have been far more sophisticated than traditionally assumed. Whatever the explanation, the results reveal a surprisingly advanced form of technological discipline. Another puzzle concerns the spread of technology itself. The Levallois technique found at Sarganagui did not emerge in isolation. Similar technologies appeared across Africa, the Middle East, Europe, and parts of Asia. This raises an important question. How did technological knowledge travel across such enormous distances during the Paleolithic? Modern communication networks did not exist. Road systems did not exist. Written records did not exist. Yet comparable manufacturing methods appeared across regions separated by thousands of kilometers. Researchers have proposed several possibilities. Perhaps populations migrated and carried knowledge with them. Perhaps neighboring groups exchanged ideas through repeated contact. Or perhaps similar solutions emerged independently in different locations. Each explanation presents difficulties. The archaeological evidence remains incomplete, leaving one of prehistory's greatest mysteries unresolved. How information moved through the ancient world long before civilization itself existed. Geological analysis has revealed that not all raw materials found inside Sarganagui originated near the cave. Some stone appears to have been transported significant distances. This may not sound remarkable today. For Paleolithic hunter-gatherers, however, it is extraordinary. Transporting stone over dozens or even hundreds of kilometers requires planning, knowledge of resource locations, and organized movement across large territories. The phenomenon resembles patterns seen at Stonehenge, where certain blue stones were transported over distances exceeding 200 kilometers. The scale is much smaller at Tsagaan-Agui, but the principle is similar. People deliberately acquired materials that were not locally available. Why? Did distant stones possess superior mechanical properties? Were they traded between groups? Did they carry symbolic significance? Archaeologists still debate the answer. The Gobi region is among the most extreme environments inhabited by humans. Temperatures can vary dramatically between seasons, water sources are limited, and food availability fluctuates constantly. Yet evidence suggests that humans repeatedly return to Tsagaan-Agui over tens of thousands of years. This implies the existence of survival technologies that remain largely invisible in the archaeological record. Stone tools survive, knowledge does not. Researchers can reconstruct hunting strategies, but many details remain uncertain. How were seasonal migrations planned? How are resources stored? How is information about water sources transmitted? How did groups coordinate movement across vast landscapes without maps? These challenges are difficult enough for modern survival experts. For Paleolithic populations, they required remarkable environmental knowledge. The cave preserves evidence of success, but reveals little about the systems that made that success possible. Perhaps the most profound mystery concerns human intelligence itself. Creating a Levallois tool requires several advanced mental abilities, including long-term planning, spatial visualization, understanding cause and effect, sequential problem-solving, and prediction of future outcomes. These are characteristics often associated with modern engineering. Some researchers argue that the artifacts from Tsagaan-Agui provide evidence that human cognitive abilities had already reached surprisingly advanced level by this period. The implication is significant. For decades, prehistoric humans were often portrayed as intellectually primitive. The evidence from Tsagaan-Agui suggests something very different. The makers of these tools were capable of abstract thought, complex learning, and technological innovation. The cave may represent not merely a shelter, but a record of the emergence of modern human cognition. One reason Tsagaan-Agui is so important is its position within a broader technological transition. The archaeological layers document changes in tool production over time. Older industries gradually gave way to newer forms of technology. This transition mirrors similar developments observed across Eurasia during the late Pleistocene. But researchers still debate how these transformations occurred. Did new populations arrive carrying different technologies? Did local populations innovate independently? Or did ideas spread through long-distance cultural exchange? The answer remains uncertain. Comparable debates surround famous sites such as Denisova Cave and Blombos Cave, where evidence of technological and behavioral change continues to challenge traditional models of human evolution. Tsagaan-Agui contributes another crucial piece to this puzzle, yet many pieces are still missing. Unexplained in central Sweden is a giant mound rising from the landscape, surrounded by stone ships, standing stones, and ancient roads. For more than 1,000 years it has dominated the horizon. But the greatest mystery is not its size. It is how its builders chose this exact location with astonishing precision long before modern surveying existed. Located near Västerås in Sweden, Unexplained has been known for centuries. Archaeological investigations conducted throughout the 19th and 20th centuries reveal that the site is not simply a burial mound. It is an enormous ceremonial complex dating primarily to the migration period and Viking Age, roughly between the 5th and 11th centuries AD. Today it remains the largest burial mound in Sweden. At first glance, Unexplained appears to be a single mound. In reality, it is part of a vast engineered landscape. The main mound measures approximately 64 meters in diameter and rises about 9 meters high. Estimates suggest that thousands of cubic meters of earth and stone were moved during construction. Even today, moving such volumes would require heavy equipment. For comparison, many famous Scandinavian burial mounds are significantly smaller. The monumental mound at Old Uppsala reaches impressive dimensions, but Anundskog remains among the largest earthworks ever constructed in Sweden. The obvious question follows: how did a society without cranes, bulldozers, or mechanized transport mobilize enough labor to create such a structure? Archaeologists believe construction would have required careful planning, resource management, and coordination among large groups of workers. Yet no written instructions survive, no engineering plans exist, and while the monument remains, the knowledge behind it does not. The name Anundskog literally means Anund's mound. For centuries, local traditions associated the site with a legendary king named Brot Anund. However, no archaeological evidence has conclusively identified the individual buried beneath the mound. In fact, researchers cannot even confirm whether a single ruler was buried there. Some scholars believe the mound was built to honor an exceptionally powerful king, while others suggest it may have functioned as a symbolic monument representing political authority rather than an actual grave. This uncertainty creates a fascinating paradox. The largest mound in Sweden may commemorate someone whose identity has been completely lost. Of all Anundskog's mysteries, this may be the most astonishing. The location appears almost perfectly chosen. The monument occupies elevated terrain overlooking a broad section of the surrounding landscape. From the mound, visibility extends across important travel corridors that connected settlements throughout central Sweden. Modern topographic studies show that the site commands a strategic position within the local geography. This raises a profound question. How did people living more than 1,000 years ago identify such an ideal location? Today, engineers use satellite imagery, GPS, digital elevation models, and computer simulations to evaluate terrain. The builders of Anundskog possessed none of these tools, yet they selected a site that combines visibility, symbolism, accessibility, and long-distance prominence. This level of landscape awareness appears repeatedly throughout the ancient world. The builders of Stonehenge selected a location connected to natural pathways and astronomical alignments. The creators of Newgrange positioned their monument to interact precisely with the winter solstice sunrise. The architects of Machu Picchu integrated their city into mountain ridges with extraordinary precision. Anundskog belongs to the same category of ancient engineering puzzles. Researchers have proposed several explanations. Perhaps generations accumulated detailed knowledge of the terrain through observation. Perhaps ritual traditions dictated the placement. Or perhaps ancient Scandinavian surveyors possessed practical techniques that have not survived in historical records. Experimental archaeologists have demonstrated that surprisingly accurate measurements can be achieved using ropes, wooden poles, sighting markers, and simple geometry. However, translating such methods into the placement of a monumental complex remains difficult to reconstruct. The precision becomes even more impressive when considering that Anundskog was not designed in isolation. The mound aligns with a broader ceremonial landscape that includes roads, standing stones, and stone ship settings. This suggests deliberate planning on a scale extending far beyond a single structure. The builders were not simply constructing a mound, they were designing an entire visual and symbolic environment. Flanking the mound are several remarkable stone ship settings. These structures consist of large stones arranged to resemble the outline of ships, and some exceed 50 meters in length. Creating these formations required much more than placing stones randomly. The builders had to maintain symmetry across long distances while preserving the recognizable shape of a vessel. Without modern measuring equipment, this would have required considerable skill. Researchers continue debating their purpose. Some interpret them as symbolic vessels carrying the dead into the afterlife, while others believe they may have served ceremonial, political, or territorial functions. What remains clear is that the builders possessed a sophisticated understanding of geometry and spatial organization. Many of the stones at Unexplained weigh several tons. Transporting such blocks presents a serious engineering challenge. Ancient Scandinavians had no steel cranes, no hydraulic systems, and no industrial machinery. The leading theories involve wooden sledges, rollers, ropes, and winter transport across frozen ground. Experiments have demonstrated that these methods are possible. Yet possibility does not equal certainty, and researchers still debate the exact techniques used. The mystery resembles questions surrounding the transportation of megaliths at Stonehenge or the movement of statues on Easter Island. Across the world, ancient builders repeatedly achieved feats that seem disproportionate to the technologies traditionally attributed to them. Perhaps the most overlooked mystery is the overall design of the site. Unexplained is not merely a mound, it is a carefully organized complex. The mound stands at the center, stone ships occupy strategic positions nearby, standing stones create visual markers, and ancient roads connect different elements of the landscape. Even the famous runestone erected during the Viking Age appears integrated into the broader ceremonial environment. Such organization implies long-term planning. It suggests that generations may have contributed to a shared vision extending across centuries. The challenge for archaeologists is understanding how this knowledge was transmitted. No manuals survive, no blueprints remain, yet the results are still visible. What do you think? Did the builders of Unexplained rely solely on knowledge passed down through generations, or did they possess sophisticated surveying and planning techniques that we still do not fully understand today? Let us know your thoughts in the comments below. On the northern coast of Denmark, overlooking the narrow waters of the Limfjord, lies the largest Viking ring fortress ever discovered. Known as Aggersborg, this enormous circular structure was built around AD 980 during the reign of King Harald Bluetooth. Yet nearly 1,000 years after its construction, the fortress continues to raise a disturbing question. How did Viking builders achieve a level of geometric precision that seems closer to advanced surveying than medieval construction? The mystery begins with a circle. Aggersborg was first recognized as an ancient fortress during archaeological investigations in the 20th century. Excavations revealed a vast circular earthwork approximately 240 meters in diameter, surrounded by a defensive rampart and intersected by perfectly aligned roads. Further excavation uncovered the foundations of 48 longhouses, arranged in a highly organized pattern unlike anything previously known from Viking Scandinavia. At first glance, Aggersborg appears to be a military fortress. The deeper archaeologists investigated, however, the more they discovered evidence of planning, geometry, logistics, and engineering that remains difficult to explain. The greatest mystery is the circle itself. Modern aerial photography reveals that Aggersborg forms an almost perfect geometric ring. The fortress measures roughly 240 meters across, creating a circumference of more than 750 meters. Maintaining such precision across an area exceeding 45,000 square meters would challenge even experienced surveyors without modern instruments. Today, engineers would use laser equipment, GPS systems, total stations, and computer modeling. Yet Viking builders possessed none of these technologies. Somehow, however, they established a circle whose geometry remained remarkably consistent throughout the entire structure. researchers generally assume that builders used a central stake and a long measuring rope. While this explanation sounds simple, practical experiments reveal enormous difficulties. A rope stretched over distances exceeding 100 meters naturally sags, twists, expands when wet, contracts when dry, and accumulates measurement errors. Even a small deviation near the center could create significant distortions along the outer perimeter. Experimental archaeologists attempting to recreate large circular earthworks have found that maintaining accuracy becomes increasingly difficult as scale increases. The larger the circle, the more every small error is magnified. This raises an uncomfortable possibility. The builders of Aggersburg may have possessed surveying methods that are only partially understood today. The mystery becomes even deeper when examining the fortress layout. 4 gates were positioned almost exactly along the cardinal directions. Massive roads intersected at the center, dividing the fortress into 4 identical quadrants. Within these quadrants stood 48 longhouses arranged according to a standardized plan. The level of symmetry is extraordinary, and such precision invites comparison with some of history's most famous examples of ancient geometric planning. The Great Pyramid of Giza is aligned to true north with an error of only a few arc minutes. Roman military camps followed highly standardized geometric layouts across vast territories. The city of Teotihuacan in Mexico was planned according to a carefully controlled urban grid. Aggersburg appears to belong to this same tradition of large-scale geometric organization. Yet unlike Egypt, Rome, or Teotihuacan, Viking Scandinavia left almost no written engineering manuals explaining how such work was accomplished. This absence of documentation creates one of the most fascinating technological mysteries in Northern Europe. How exactly did Viking surveyors establish accurate cardinal directions? One possibility involves astronomical observation. By tracking the sun's shadow at noon, builders could approximate north-south alignment. Another theory suggests observations of Polaris, the North Star, which already served as an important navigational reference for Viking sailors. However, determining direction for a single point is one challenge, while transferring that accuracy across a fortress spanning nearly a quarter kilometer is another entirely. Even modern construction projects require continuous verification to prevent cumulative errors, yet Aggersburg's builders appear to have achieved precisely that. The fortress also demonstrates an astonishing degree of standardization. Excavations revealed 48 longhouses arranged in identical patterns. Each measured approximately 32 meters long and 8 meters wide, and their positions were carefully coordinated with the road network and surrounding defensive works. This suggests the existence of standardized measurement units. Archaeologists have long debated whether Viking builders used a common surveying module. Some researchers propose that the dimensions found at Aggersburg, Vierkat, Trelleborg, and other ring fortresses were based on a shared geometric system employed throughout Harald Bluetooth's kingdom. If true, the implications are significant. A standardized measurement system would indicate centralized planning, trained surveyors, and a level of administrative control far beyond traditional stereotypes of Viking society. The engineering challenge becomes even more impressive when considering construction logistics. The ramparts surrounding Aggersburg required enormous quantities of earth, timber, and labor. Thousands of trees would have been harvested, transported, processed, and incorporated into the structure, while massive volumes of soil had to be excavated and moved without mechanical equipment. Some estimates suggest that construction may have required tens of thousands of labor days. To appreciate the scale, consider that medieval European castles often took decades to complete. Yet evidence suggests that Aggersburg may have been constructed within a relatively short period during Harald Bluetooth's reign. This raises another unanswered question. How was such a massive workforce organized? The Viking Age is often portrayed as a period dominated by local chieftains and regional power centres. Aggersburg instead suggests centralised command, coordinated resource distribution, and sophisticated project management. In many respects, the fortress resembles a military infrastructure project rather than a traditional settlement. Yet the purpose of Aggersburg remains surprisingly uncertain. The fortress could accommodate thousands of people. The 48 longhouses alone provided substantial housing capacity, and its strategic position overlooking the Limfjord allowed control of one of Denmark's most important transportation roads. Many historians interpret Aggersburg as part of Harald Bluetooth's effort to unify Denmark and strengthen royal authority. Others argue that it functioned as a military staging base for campaigns directed towards Norway or England. A more intriguing possibility is that the ring fortresses formed a coordinated network. Aggersburg was not alone. Other circular fortresses, including Trelleborg, Fyrkat, Nonnebakken, and Borgring, share remarkably similar geometric principles. Despite differences in size, they display nearly identical design concepts. This consistency suggests centralized planning on a national scale. If the fortresses were constructed according to a common blueprint, who designed that blueprint? No architect's name survives. No construction manual survives. No engineering diagrams survive. Only the structures themselves remain. Recent archaeological studies using high-resolution LiDAR mapping, geophysical surveys, and digital terrain analysis have only intensified the mystery. These technologies continue to reveal subtle geometric relationships that are difficult to attribute to chance. The more precisely Aggersburg is measured, the more impressive its design appears, and that leads to perhaps the greatest mystery of all, the lost knowledge. The builders clearly understood large-scale geometry, surveying, logistics, standardized construction, defensive engineering, and project coordination. They transformed these skills into one of the largest architectural achievements of the Viking Age, yet almost nothing survives explaining how they did it.